speed of sound locally. Yeah. So it's the air flowing over the wing when it reaches that point where it's accelerated to the speed of sound, whatever the speed of sound is locally. Yeah, so obviously if you're flying at 30,000 feet, the speed of sound is going to be different to if you're flying at sea level. You see what I mean? Has that answered your question?
Okay.
Yeah, so theoretically you could say sonic, but because to make life simple, and that's why we use Mach. Just think of it in terms of Mach 1 is the true speed of the aircraft, as the relationship between the true speed of the aircraft and the speed of sound locally. So those that have just joined us, good morning, namaste. Before we kick on, as we've just been discussing there, has anybody got any questions at all from anything that we covered last week?
Yes, Jim.
Yes, Suresh.
I have some question from pressurization. And when
Pressurization?
Yeah,
go on.
I'll speak. There is a question: which component control the cabin altitude? Is it simply a discharge valve, outflow valve?
Yes.
Okay.
Yeah, the discharge valve.
Okay. And another question, I'm confused. If the aircraft has established the cabin altitude and this is also a maximum differential pressure, what happens if the aircraft climb to a higher altitude?
It does tell you in the notes. The cabin altitude will adjust, if I remember rightly.
Okay.
I haven't got the notes open at the moment, but it's definitely in there. And if you exceed the maximum altitude, then the cabin altitude will adjust accordingly to keep you within the limits.
Okay.
Yeah, the discharge valve and the cabin altitude controller. You set the cabin altitude on the controller,
Yes.
and it's the cabin altitude controller that's telling the discharge valve when to operate.
Okay.
Yeah, so it's a dual thing for controlling the cabin altitude. It's the controller that's controlling it, but it's doing it by speaking to the discharge valve.
Okay, Jim. Okay, I have another question from M11.
Yeah.
In M11, the control column movement will make the M11 as to act as elevator control column.
Yeah.
And the control will, the movement of control will make the M11 to act as an aileron.
Yes.
And if in the case when we want to climb the aircraft, or and at the same time we want to like roll the aircraft, do we need to make the input from both control column and control wheel?
Yes, because if you're climbing the aircraft, you're going to be pulling back on the control column.
Okay.
Then when you want to turn the aircraft, you're going to turn the hand wheel. So the control column will be pulled back, and then you turn the hand wheel to turn your aeroplane.
Okay. Because I'm confused. In the last line, there is the control system are interconnected so that M11 can be moved to produce the pitching and rolling moment at the same time.
Yeah.
Okay.
So if you've pulled back on the
Yeah, I got.
Yeah, that's your control column.
Control column. Okay, okay.
So
now
yeah,
I got Jim. Thank you.
Pull back on the control column.
Okay.
That's going to put the elevators up, or the elevons up, push the tail of the aircraft down, bring the nose up. If you want to then roll the aircraft, yeah, you're going to turn the hand wheel, yeah, so backwards and forwards, or left and right. So the hand wheel, yeah, you're going to turn that left or right. The control column, you're going to move forward or aft. Yeah. If you look at the sort of the back of the aeroplane, yeah, your elevons will come up together to give you your pitching motion, or they will act independently as ailerons. Yeah.
Okay, Jim. Okay, I got now.
Okay.
Okay, thank you, Jim.
It's okay.
Yeah.
Anybody else got any questions at all on anything from last week? No, right, lovely. In that case, we will plod on with our flight controls. I think we've got today to get through them, and then we've got landing gear for tomorrow and Wednesday. And the B2s will be glad to know that's the end of their mechanical side of things. So what we're going to look at this morning are our powered flying control systems. We looked at the mechanical systems last week, and the mechanical systems geared up control cables attached to the control surfaces. So as the pilot moves the controls, he's got sufficient strength and sufficient leverage through the system to be able to operate those controls. He does get assistance aerodynamically from his balance tabs, but the larger the aircraft now, as we step up and increase the size of the aeroplane, it'd be physically impossible for the pilot to move the controls. He wouldn't be able to overcome the aerodynamic forces. So what we're going to do is to use hydraulic power to either assist him or to operate the controls for him. Kind of depends on the size of the aeroplane, and that hydraulic assistance comes under the umbrella powered flying controls. Sort of controls that we're going to operate with that power assistance or that power operation. Normally your primary flying controls, your ailerons, your rudder, your elevators, your spoilers we can operate hydraulically, and again our leading and trailing edge devices. The control surfaces, as we go into the powered side of things, we'll split up the control surfaces. We'll duplicate them and duplicate the hydraulic systems just in case of failure. So the effort of the pilot not sufficient to cause movement of the controls, so we're going to use hydraulic power to assist him. Many types of large aeroplane, the control surfaces are arranged in pairs. Again, as a backup feature that ensures good control, low and high speeds, and ensures that we've got control of the aeroplane if we do get any failures. Spoilers we've already mentioned. We can put spoilers on the aircraft. We can either use those to give us roll control, or we can use them to assist the ailerons in giving us roll control. Elevator rudder duplicated, again as a safety precaution. And then on delta wing aircraft, we've got the elevons that we talked about, and that Suresh has just been asking about. So while the control wheels turn clockwise, anti-clockwise, we're going to get one elevon raised, the other's lowered, just like your ailerons. If we pull the control column back, the elevators are going to move together, or the elevons are going to move together and act as elevators. While we're in that condition, if we pull back on the control column, the aircraft's climbing. If we want to roll, we'll put a hand movement, hand wheel input in, and the elevon on one side will lower slightly. Pardon me. Will lower slightly, which will give us that rolling movement, rolling motion. Yeah. Again, just an example of your delta wing aircraft, just showing that the elevons all duplicated. Will act as elevators, will act as ailerons. The rudder surface is duplicated to give us that directional control, and again the rudder duplicated to if you had failure in one system, the other system would kick in and help out. And also with the rudder, another reason for the two-part rudder is so that you're not putting that whole slab straight into the airflow. We've got more control over the rudder that way. So powered aircraft, talk about powered aircraft. That's again your elevons, and I only put that in because it's my favourite picture of my favourite aeroplane of all time. So aircraft flying at high speed, the loads on the control surface is beyond the capabilities of the pilot. Physically, you couldn't move them, so we're going to give that hydraulic assistance to move the controls. We can do that hydraulically. It says electric actuators, but normally it's going to be hydraulics. Moving the control column of the rudder pedals puts an input signal to the output of the actuator, which moves the control surface. Transmission of the pilot's input to the power control actuator will be done mechanically using cables or push-pull rods, or in the more modern aircraft we can use fly-by-wire. So we're going to put electrical inputs into the actuator, and then we're going to get a hydraulic output out of the actuator. There are two types of power control that we'll use. Power assisted, and in a power assisted system, the pilot, as the name suggests, he's putting the input in and he's getting help from the hydraulics to remove the or to move the control surface. So his force is backed up by hydraulic power. With the power assisted system, and we'll talk about in a minute, the pilot will get feedback from the control surfaces. So as he moves the control surface, the aerodynamic loads on that control surface will be felt back through the linkage, through the control system, and the pilot will be able to feel how much effort he needs to move the aeroplane. It's a bit like when you run along on your bike or your car. As you turn the steering wheel or turn the handles, you know how much movement you've got to put in to get how much movement out, and you can feel the amount of movement you're putting in back through the road. With the aircraft, it's the aerodynamic loads on the control surface that is felt by the pilot, So he knows how much to control, or how much to turn the control handle, or how much to pull back for how much output he's going to get. The other type of system we've got is the power operated system. And with the power operated system, the control surface is moved totally by hydraulic power. The pilot just puts in the input to move a little servo valve in the actuator. So it's hydraulic power that moves the control surface. There is no aerodynamic load felt back through the system. So the pilot we need to provide artificial feel for the pilot. All he's doing is moving a little valve. With the power assisted, he's actually getting that feedback through the system. Yeah. So with our powered controls, then, yeah, the system needs to be safe. It needs to be positive, and it needs to be instinctive. Yeah, safe. We don't want it failing on us. We don't want any mishaps, failures. So part of that safe bit is to provide backup in the event of an emergency. Needs to be positive. So if I put an input in, I want an immediate reaction. I don't want to be waiting half an hour. An instinctive, yeah, if I push the stick forward, I want the nose to go down. If I pull the stick back, I want the nose to go up. We also need the system to be sensitive, stable. We've got that irreversibility, so we need feel, and we need backup as well. So let's see what we're saying then. Yeah, with when we talk about sensitivity, yeah, if I put an input in, I want an immediate response. Yeah. So sensitivity is to give the immediate operation of the unit without a time lag there. And we'll look at the picture in a minute, but we managed that by what they call minimum valve overlap. Let's just little. Your minimum valve overlap, the ports in the actuator, yeah, you've got these little drillings, these little tappings that are allowing fluid into the ram area of the actuator. And the way we get that immediate response is by what they call minimum valve overlap. If I had a large covering, if you imagine the pink bit's the port, and the yellow bits are a piston on a little valve. If I had a large amount of overlap, it would take quite a lot of movement before I'd allow hydraulic fluid into the port. So if you imagine your red's your hydraulic fluid, your yellow's your little piston, your pink's your outlet. That yellow piston is covering the outlet port. So if there was a large overlap between the piston and the port, it'd take a large movement of the piston to allow hydraulic fluid through. With minimum valve overlap, the machining and manufacture is very, very, very precise. So we've got the absolute minimum difference between the port and the spool. So now if I move the valve just the tiniest amount, then we're going to admit hydraulic oil into the piston chamber of the actuator. So we're going to get that immediate response. Yeah. So on page 67 at the top there, when we're talking about sensitivity, yeah, sensitivity obtained by using minimum valve overlap. Yeah, and that is again worth your highlighter. Stability of the actuator. We want the thing to respond to inputs from the pilot. We don't want anything else interfering. So the stability side of things is making sure that there's no outside influence is going to move the control surface. With it, we get rid of any backlash in the system, certainly keeping the system free from air. If we had air in the system, that could cause your control surface to move because you'd just be compressing air rather than hydraulic oil. And putting dampers in the system as well. Yeah, dampers. So when we reach the when we reach the selected position, what I don't want is the hydraulics start to bounce backwards and forwards. So we put these little dampers in the system as well. Irreversibility, it means that the air loads on the control surface shouldn't be able to move it. And the way we achieve that is to make sure that there's a hydraulic lock within the power unit. Please note that your fully powered flying controls are irreversible. The power assisted controls are reversible because you get that feel back through the system. So your irreversibility means nothing is touching those controls. There's no feel back through the system for the pilot, but with power assisted, there is. Some of the air loads are felt via the control linkage from the control surface, felt by the pilot. What else have we got? We've got feel. We need to provide feel. So as the pilot's moving the control surface, he needs to know how much movement at the stick is going to give him how much movement of the aeroplane. And an experienced pilot will know that through the feedback that he gets through the control system and how much resistance he's getting to his movements. As we said, with a power operated system, we don't get that because all the pilot is going to all he's doing is moving a little valve in the actuator. So with a power operated system, we need to provide some sort of artificial feel for him. So he knows how much movement of the stick is going to result in how much movement of the aeroplane. Just try to think of an analogy. It's a bit difficult out with the classroom, but if you've got a desk in front of you, you know how much force you've got to apply to push that desk, let's say half a meter. You want to move the desk half a meter, you know how much force you've got to apply to get that desk to move. If you're just standing there and you get somebody else pushing the desk, you haven't got that feedback, you haven't got the resistance, so you don't know how much force you need to apply if somebody else is pushing the desk, which is why we need to build in that artificial feel, so you can feel the resistance, simulate the resistance of the airflow, so we know how much force we've got to apply to maneuver the aircraft. So, kind of makes sense?
Yes, Jim.
Yeah.
Yes, Jim.
Okay. Right. The other thing that is critical in a power operated, power assisted system is backup. If we have a failure in the hydraulic system, we still need to be able to maneuver the aircraft, still need to be able to get it done down on the ground. So with our backup, to ensure that we can operate the aircraft, we can either go to a manual reversion. That can be very difficult on larger aircraft because the pilot just doesn't have the physical power to move the controls. However, with some of the power assisted we can revert to manual. More commonly, we're going to duplicate everything. Yeah, so we're going to duplicate the power units, the power supply. When we're talking power, the hydraulic systems. Yeah, so if we do get a failure, we can isolate the failed system, and we can use a secondary system to operate the controls for us, so we can get the aircraft down safely. So those are the requirements of our flying control system: the sensitivity, stability, irreversibility, feel, and backup. Yeah, immediate operation, minimum time lag, no outside influences. Yeah, the air loads on the surface not pushing the surface back, not moving the control surface. The feel, the degree of deflection and speed, and how the air flows loading on the controls, and backup. Yeah, if we've got a failure, then we need to be able to address it. As we said, there's two types of control: the power assisted and the power operated. Yeah. We don't need to worry too much about the ins and outs of the actuator, but there are a couple of bits that we need to highlight so we can understand what's going on. With the power assisted actuator, we are giving hydraulic assistance to the pilot to move the control surface. So the control column, yeah, the stick via the linkages and through the actuator, the stick is connected directly to the control surface. Yeah, so now if I move the stick, again, I'm moving the link, which in turn is allowing hydraulic pressure to assist the pilot to move the control surface. To get that hydraulic power, we've got an input, and in the actuator we've got what they call the servo valve. This is a very simple system, and the servo valve connected to the control column. As the pilot moves the control column, he's moving the servo one way or the other. So in this case, if he moves the stick back, yeah, he's going to move the servo valve. Yeah, and by moving the servo valve, he's allowing hydraulic pressure into the actuator body. With this type of actuator, the body is going to move. Yeah, the ram is again via a linkage. The ram is fixed to the aircraft structure, so that ram can't move. As I allow pressure into the ram chamber, that pressure acting on the ram and acting on the actuator body is going to cause the actuator body to move, which in turn is moving the control surface. So it's a body mounted ram mounted actuator. The ram is mounted to the aircraft structure. As the body moves, yeah, we've moved the servo over. So now we've got pressure admitted into the chamber. The pressure is putting on, acting on the face of the actuator body, causing that actuator body to move in that direction. And as the actuator body moves, it's sealing off again. It's bringing the body in line with the servo. And as it brings it in line with the servo, now we can't admit any more hydraulic oil into the chamber. No more hydraulic pressure in there. So the thing goes into a hydraulic lock, and it will stay in that position until we make another selection. Yeah. Yeah, anything else I need to point out on there? We'll come on to it later as well, but the interconnecting valve, yeah, normally your hydraulic pressure sitting there, ready and waiting, and a spring, hydraulic pressure overcoming a spring and closing the interconnecting valve. So both sides of the actuator are separated. If I had a failure in the hydraulic pressure, there'd be no pressure on top of the interconnecting valve. The spring would push the valve piston up, seal off that inlet port. So now as I move the stick, there's a little stop in there, and that pushes the actuator body. And all I'm doing, because the interconnecting valve is now closed, I'm allowing fluid to pass from one side of the actuator to the other as I move it via the stick. So the stick via the stop is moving the body, and fluid is just passing from one side to the other. Purpose of your interconnecting valve. Is everybody okay with that? Any questions there? Any queries there? Right, so just reading through it from the notes, make sure we haven't missed anything.
Hello, Jim.
Yeah.
Jim, can you again please describe this diagram?
Yeah.
Hmm.
Yeah, I'm just pointing out the important parts that we need to know about. We're looking at power assisted control. Yeah.
Okay.
So the pilot is moving the stick.
Hmm.
Yeah, and via the actuator, he's moving the control surface, but he's getting hydraulic assistance to do that. And the way it works, the actuator ram is bolted to the aircraft structure via the control linkage.
Okay.
Pilot's control link, there's a little stop valve, so as he moves his stick backwards and forwards, that stop valve has got a bit of room. I say stop valve, it's a mechanical stop. There's a little bit of excess movement in there. That control column via that linkage is connected to a servo valve. Yeah.
Okay.
And it's the movement of the servo valve that's going to allow hydraulic pressure into one side of the ram chamber or the other.
Okay. Okay.
Yeah. So in this case, we're going to move the stick back. As the pilot moves the stick back, he's moving the servo slightly. And because of that minimum valve overlap that we talked about, now hydraulic pressure is going to be admitted into the ram chamber on the left-hand side. Because that ram is fixed to the aircraft structure, the ram can't move, it can't go anywhere. It's solid. Hydraulic pressure that comes into that ram chamber is now acting on this face of the actuator body. So it's going to cause the actuator to move. And as the actuator body moves, the control surface is moving.
Okay.
You with me there?
Okay, I got it.
Okay. So now, as the actuator body moves, the ports are going to move, and they are going to cover the servo is going to cover the ports now. Yeah. Because those ports are covered, there's no hydraulic pressure getting in and out of the ram chamber, so the actuator is in a hydraulic lock, so it will not move until the next selection.
Okay.
If I get a failure in the system, we've still got to be able to control the aeroplane. So what happens is we either turn the hydraulic power off, or the power will trip off because you've got a leak or whatever. This little interconnecting valve, when everything's working properly, hydraulic pressure is pushing down on the interconnecting valve, compressing a spring. So now that interconnecting valve is sealing off both sides of the actuator from each other. If I lose hydraulic pressure or I turn hydraulic pressure off, that piston is going to move up, and it's going to open these ports to each other. So it's going to seal off the inlet for the hydraulic input. So now if I move the stick, that stop is going to contact, let's say I push the stick back. Yeah, the stop is going to contact that face, and it's going to move the actuator body. And it can move the actuator body because as the body's moving, fluid from one side of the ram chamber is passing to the other. So that the actuator can actually move without the hydraulic power in there. It's going to take an awful lot of effort from the pilot to move it, but he's got controllability of the aeroplane. Is that okay?
Okay, Jim, thank you.
Okay. So yeah, just out the notes. Yeah, normal operation. Selection made on the selector. Fluid under pressure passes to the appropriate end of the actuator and moves to its end of travel. The other side opened up to return. Yeah. When it's talking in the notes, when I'm talking about the servo valve, it's calling it a selector in the notes. It's exactly the same thing. Yeah. So halfway down page 68, it says, given a actuator must move the control surface a required amount, hold it in the selected position. In a hydraulic selector, when a selection is made, fluid under pressure directed to one side of the actuator or the other. If during the actuator's travel, the selector is placed in a neutral position, the fluid will be trapped. So that what they're calling the selector, on the diagram, it's calling it the servo. Yeah, so don't get confused by the terminology. It's the same thing. They're just using a different name, and that's something that I must write down along with the other stuff you gave me. Yeah, so the power assisted actuator, designed so it's hydraulically locked when the given selection is achieved. The amount of movement is controlled directly by the pilot. Yeah, achieved having so that the actuator ram remains fixed. The actuator body moves. Actuator body moves, neutralizes the selector, and because the selector is neutralized, the thing locks up. Yeah, and then page 70, it's just describing the actuator, describing what's going on. Yeah, it does there say that the integral selector, the servo valve. Yeah. What's everything going on? Is there anything that we need to worry about?
Jim, which are the same terminology? Selector,
yeah,
and
when it talks about the selector in the text, yeah, the selector is described in the diagram as a servo valve. They are the same thing.
okay.
Yeah. Right. Pilots made the initial selection. Control column remains in this position. As the actuator body moves, the selector valve body moves with it until the drillings are covered, stopping the supply of the fluid to the actuator. That is known as negative feedback. I think that is highlighted in bold later on, but on page 70, yeah, about halfway down, on to the second paragraph it is, yeah. As the body of the actuator covers the ports, that is negative feedback. And the servo valve is then in a neutral position, and that locks the actuator in the position we're selected at. Control remains there until reselected. Actuator is connected to the control surface, connected to the control column, so we're always going to get that feel back through the system. Some of that load felt by the pilot, and that's known as proportional feedback. So your negative feedback, where the selector goes into the neutral position. Proportional feedback just gives some of the airload, the feel back through the system. During manual operation, actuator body is manually operated by the servo valve stop and moves over the ram. Yeah, so the interconnecting valve closes, opens both sides of the actuator to each other. So now as the pilot pushes on the stick is physically moving the actuator body, and any displaced fluid will just go from one side of the ram to the other. And again, I've just got pictures there. That was our minimum valve overlap. Please make sure that you highlight and understand minimum valve overlap. It's the servo valve, covering the port, and because the drillings and the machining of the valve are so close tolerance, any slight movement of the servo valve is going to allow hydraulic pressure into one side of the actuator or the other. If we didn't have that, there'd be far too much movement, and the thing wouldn't be very responsive. All okay with that? With our power operated control, again, we're looking at something similar where we've got the actuator bolted to the airframe so that ram can't move. The actuator body is connected to the control surface, but the big difference is there is no link between the control column and the control surface. There's no link through. So all that the pilot is doing in a power operated system is moving the servo valve. So now any loads on the control surface, the pilot can't feed them, can't feel them. So we need to give him some sort of artificial feel. The operation of the actuator is exactly the same, in as much as the pilot is moving the stick, but all he's doing is moving the servo. As he moves the servo, that is allowing hydraulic fluid into the actuator, into the ram chamber. Because the ram is bolted to the airframe structure, then the body of the actuator is going to move. So in this case, if he moves the stick backwards, forwards, he's pulling the servo to the right. As soon as he does that, that's allowing hydraulic pressure into the ram chamber. Because the ram is fixed, the pressure acting on the body is going to move the body to the right, and as the body moves to the right, then the servo ports are going to get covered. That is going to put the actuator into a hydraulic lock. Anything else I need to say there? Not really. Not really. You've still got the interconnecting valve. You've still got the stop whereby he could push and pull the actuator body to try and position the actuator, but theoretically it works, but it's awful hard for him to move a power operated control. So again, just going through the text in the notes, supplying only the power operated, pilot supplies only the force necessary to operate the servo, and then it just goes on to talk about the operation of the thing. Control column in neutral, 2 lands of the selector servo valve, cover the drillings, so fluid on both sides. Pilot moves to control column, fluid into the right hand end of the actuator, other end open to return. Yeah, fluid pressure at the right hand side moves the actuator body, which in turn the body moving moves the control surface. As the actuator body moves, the selector valve body moves with it, and the drillings are then covered up. That is your negative feedback that we've just mentioned. Yeah, interconnecting valve operates as previously described, that we've been through that. If manual reversion is an option, it's exactly the same as we saw before. Yeah, some installations, the body of the actuator is mounted to the aircraft structure. Again, a lot of it, it's a kind of design for your aeroplane. Depends on available space, all the rest of it. The ram-mounted actuators tend to be better because they are space savers. Yeah. But if you've got a body-mounted PCU, we want the servo to go to that nulled position when we've achieved the output that we want. So with the body-mounted PCU, we need to put an extra linkage in. So as the control surface reaches its selected point, yeah, the feedback lever is moving the servo again to cover the ports in the actuator. So if you can imagine moving the control column, as I move the control column via this linkage, yeah, I'm going to move the servo. Let's say we'll go that way. Hydraulic fluid now into the actuator, and because the body is fixed, the ram is going to move. So now as the ram extends, the elevator moves, but as that ram is extending, because of that follow-up link, it's moving the servo to put the servo into that neutral position. Yeah, so we're still getting that negative feedback, but rather than doing it by mounting the ram to the aircraft structure, the feedback link is when we've got the body mounted actuator. Yeah, so your body mounted actuator, follow-up principle remains the same. Yeah, PCU fixed to the airframe structure, ram that moves. Control column neutral, servo covers the ports. Yeah. Pilot moves control column, servo valve moves, allows fluid to pass to one end of the actuator, other end open to return. Actuator ram moves to, in this case, the left. Elevator is raised, but the summing lever returns the servo back to that neutral position. So we're still getting that negative feedback. Actuator hydraulically locked because the fluid's trapped in there, and it will remain in that position until another selection's made. Yeah, so just because of the follow-up link, so as the elevator's moving, yeah, the follow-up link's moving, and it is follow-up link is moving the servo to the neutral position as we move the actuator. Yeah, and again, just picture tracker shows, yeah, move the control column back. Yeah, the summing lever operates the servo. Servo shifting allows hydraulic pressure into the ram chamber. The ram moves. As the ram moves, it moves the elevator up. Yeah. As the elevator's moving up, yeah, it's moving the follow-up link. As it moves the follow-up link, that is moving the servo to cover the ports and putting everything into that hydraulic lock. says actuator's hydraulic lock because the fluid's trapped. Yep, remains there till reselected. It says, although it doesn't show it on the sketch, you can have an interconnecting valve in there, but again, it depends on the size of the aeroplane really, as to whether he'll be able to move the controls that way. Everybody okay with that? Any problems there? Right, so components, hydraulic ram, the servo valve, page 76. Yeah, what are the functions of the servo valve? The servo valve is going to give direction of movement. It's going to tell the actuator which way it's going. It's going to give rate of movement. Yeah, it's telling the thing how fast it's going to move. And it's going to give magnitude of movement, how much movement. So those are the three functions of the servo valve. Yeah, and stick your highlighter through those 3 bullet points. Servo will provide direction, rate, and magnitude. Which way, how quickly, how much. There's a damper fitted. It doesn't show the damper on the sketches that we've got, but you can imagine if we, it doesn't matter what type of actuator, as we move the actuator, you're getting full system pressure going into one end. Yeah. As the servo valve shuts off, there's a possibility that you're going to get bounce in the actuator. So what they do is just put a damping mechanism in there just to ensure that you've got nice smooth movement of the actuator. The interconnecting valve we've already talked about, allows manual control, or with the interconnecting valve, wherever we are, with your power operated system, yeah, if you've got a failure in your actuator, if you've got duplicated actuators, by shutting off the hydraulic system, yeah, a second actuator can move the control. This would just become a damper effectively. So fluid would just pass from one side of the ram to the other as another actuator is moving the control surface. Yeah, so your interconnecting valve. Right. You can imagine the carnage that could be caused if that servo valve got stuck. Yeah, so there's always a possibility the servo valve could stick. So what we need to do is to put in some sort of warning. Yeah, so we can let the pilot know that he's got a stuck servo valve. He's got a duff actuator. So now he can deselect that actuator and take it out of the system. So a stuck servo valve isn't putting a constant input into the actuator. Yeah, so what we do is put stuck servo detectors into the system. Yeah, should a servo valve see stuck valve detector will stick on a warning on the CWP. We can then deselect the damaged system. We can turn the damaged system off, and other hydraulic actuators can carry on controlling the aircraft. Right, not a fantastic picture, but the idea of the stuck servo detector, yeah, we're going to get inputs into 2 or 3 actuators operating a control surface. In this case, it's 3. The stuck servo valve is just a little micro switch, basically. Yeah. So as everything's working fine, yeah, what I've got is a hydraulic clutch in the system, just allowing fluid through into the servo. One end of the servo connected to the stuck servo detector. Yeah, while everything's working fine, the servo's moving backwards and forwards, and it's allowing fluid into the actuator. Should the servo valve stick for whatever reason, as we try to move the actuator, yeah, that's going to cause this detector strut to put a light on in the cabin. The pilot can then deselect the Duff hydraulic system. Yeah, that little clutch will operate, and that will isolate the bad actuator. Yeah, so stuck servo struts between the servo valve and the input. Yeah, should a servo valve seize, the stuck valve detector struts compress or extend to operate a micro switch, illuminates a warning on the CWP. Other systems will continue to operate, but with a slightly higher stick force because you've taken away some of that hydraulic power. Hydraulic clutch is incorporated into each of the actuator servos, engaged when the system's pressurized, released if the power on-off valve is operated to depressurize or unload the system. So when the pilot unloads the faulty system, the clutch is released. The remaining two control systems operated as normal without increased stick forces which are present until the system's unloaded. They say the system is fail-safe, so a stuck servo valve can't prevent the flying control operation. Any two actuators can overcome the third, as well as move the control surface. Yeah. So again, yeah, the stuck servo valve detector. Where's me light? Yeah. As the valve's moving, fine. If the valve sticks, yeah, it's going to put an input in, either pulling or pushing. Servo detector, that will put on a warning in the CWP. The other two systems will carry on operating the flying control. The clutch will disengage, and as the clutch disengages, hydraulic power is removed from the failed actuator, and that just gets dragged backwards and forwards by the other two operating as normal. Yeah, your stuck servo valve detector. The other type we've got where the servo actually runs in a little sleeve, the little blue sleeve. So long as everything's happy, yeah, if the servo valve is moving all right, everything's happy. Should the servo valve get stuck for whatever reason, yeah, as force is applied, the servo is going to carry the little blue sleeve. And as that moves, it's going to operate a micro switch, which again is going to have the same effect. It's going to put a light on in the cabin to tell him he's got a Duff. A Duff servo, yeah. So again, he can turn the power off, yeah, and he can either deselect the system or it'll go into an automatic damping mode. Yeah, so PCU designed such a way that servo valve slides within a ported sleeve. Should the servo valve seize, ported sleeve moves, directs hydraulic supply pressure to return, allowing the PFCU to idle. Movement of the ported sleeve also operates the micro switch, putting on the warning light in the cabin. So that little sleeve, yeah, works fine. Servo sticks, that'll move, operate the micro switch, but it'll also open up the actuator to return. The reaction linkage is in there for every action, equal and opposite reaction. Yeah. So as the power control unit is extending and retracting, operating the control surface, the force that it's extending and retracting is going to be felt on the attachment point on the aircraft structure. Eventually, that's going to lead to a build-up in stress, the reaction load, and that could damage the the aircraft structure. So what they do on a lot of actuators, they'll put in the a little link from the structure end to the control surface. So now as the PCU extends or retracts to move the control surface, as the control surface is moving, that movement is being felt at the reaction linkage. So what we're doing is we're taking that reaction force and just sharing the load out, if you like. It reduces the reaction loads at the spar end. So it's just there to relieve some of the stress on the aircraft structure. That is the reaction link. That's the purpose of it. We'll see a similar thing later on with our landing gear. The transfer valve. I'll just do this bit, and then we'll have a cup of tea. Yeah, the transfer valve is there to allow inputs from things like autopilot into the actuator. Yeah, and all your transfer valve is a little bolt-on package that moves a little actuator within the main actuator. If I put a wiggly line down there, yeah, which I'll get rid of in a minute. Forget that for the time being. This side of the actuator is just what we've been talking about. We've got the input from the control. The input from the control is moving the servo valve. As the servo valve moves, it's allowing pressure into one side of the actuator ram chamber or the other, and as pressure goes in, it's moving the control surface. Okay with that? Yeah, so that side we can forget about. We've seen that, we know how that's working. Yeah. Now, chop down there just for a minute. Forget that bit. Yeah. Within the transfer valve, yeah, what we've got is from the autopilot, we've got an on-off solenoid from the main hydraulic system. We turn the system on, yeah, and that solenoid is going to allow pressure up to, oh look, calls it a spool valve here, but it's another servo. Yeah, and that servo is sitting there with pressure at either end, locked in a neutral position. The autopilot, yeah, again we take a tapping from the main hydraulic system, and that tapping goes to what they call well, it says flexible tube here, just a little pipe with a hole in the end. Yeah, that pipe is operated by a position of it is operated by a magnet. So your autopilot, we'll say autopilot, wants to move the aircraft. It'll send a signal to this little magnet, and as the magnet operates, yeah, it's going to either repel or retract, which is going to cause this little flexible tube to move one way or the other. As it moves, it's directing more pressure to one end of the spool valve than the other. So let's say we go this way. So it'll push the spool valve down. Yeah, that in turn is going to allow hydraulic pressure, the hydraulic pressure that was sitting there ready and waiting, into the autopilot actuator. The autopilot actuator is putting a feed into the main arm there, and as it does, the actuator is going to move. So now That actuator moves. Yeah, that's causing the main servo to operate the flying control. The end of the autopilot actuator is a transducer, a linear variable. Can't remember what D stands for. I'll come across it in a minute. Variable transducer. Yeah. So as the actuator is moving, again we've got a transducer for the position of the actuator. So as that's moving, it's sending a feedback to the autopilot system. The autopilot system reducing the input, yeah, on the transfer valve, and as the input goes back to a neutral, you've got the same area either end of the spool valve. That's going to close it off. It's going to lock it in the neutral position until we're ready for the next selection. And that's all your transfer valve is doing. It looks complicated. Trust me, it isn't. Yeah, so your transfer valve, yeah, operated by the pilot or by the autopilot. Autopilot engaged, on-off solenoid opens, supplying pressure to the transfer valve. Autopilot transducer indicates how far the actuator has been moved by the operation of the transfer valve. Control surface transducer indicates position of the control surface. Yeah. And then it just goes through to describe what's happening, which I've just done, and hopefully everybody was on board with that. Nothing else there that we need to worry about. Yeah. Tandem actuators. Somebody asked about tandem actuators the other day, actually. Yeah. A tandem actuator, what we're going to do is run two systems through one jack. Yeah. And the tandem actuator, everything's duplicated. We've got two servo valve inputs, one from system A, one from system B. Two hydraulic systems, system A, system B. Those hydraulic systems acting on the servo. Yeah. Two identical rams in separate chambers in the actuator, and all attached to our control surface. So long as we've got pressure coming in on both actuators, yeah, we'll put an input in. As the input comes in, that input is going to move both servos at the same time. Yeah, so both rams are going to move at the same time to move the control surface. If I get a failure in, let's say, system A for whatever reason, system B, I am still moving the servo valve, and that servo valve is now operating the actuator via one piston chamber. Yeah, so tandem actuator, double-ended actuator, each one has its own servo, ram, hydraulic supply. One supply is not available, sufficient power available from one supply acting on one half of the actuator to operate the control surface. So it was transfer valve, just allowing us to operate from different places. Has anybody got any questions on any of that? Any questions on your powered flying controls? Eh?
Sir, please
Sorry, I can't hear you. Very, very broken.
Sir, tandem system, sir. Tandem flying system.
No, still not hearing you. Speak slowly and speak loudly.
He wants you to explain tandem.
Tandem actuator, yeah.
Sir,
What you've got is one actuator, yeah, one actuator body, but within that body you've got two separate systems. Yeah, so system A, yeah, has got its own hydraulic feed. Yeah, the actuator has got a servo that reacts for system A. It's got a ram that reacts for system A. System B got its own hydraulic pressure system, and in the actuator, again, it's another servo bolted onto the top of one body. We've got a servo valve for system B, and within the one body, again, we've got a ram for system B. So long as everything's working, the two of them will work together quite happily. If I get a failure in system A, yeah, so both of them are working quite happily. I move the stick, yeah, as the stick moves, it's going to move the servo, yeah, as it moves the servo, it's allowing pressure into the actuator so that the rams are going to move in the same direction to move the control surface. Should I lose a system, let's say I lose system A for whatever reason, it's got a leak in it, yeah, there's no pressure getting to system A. If I move the stick now for system B, exactly as we've seen before, hydraulic pressure, yeah, because of that interconnect, system B servo will still be operating, still be responding to the pilot's inputs. Response to the pilot's inputs is feeding pressure into the system B ram chamber, and it's now the system B ram that's going to be moving the control surface for us.
Okay,
Okay
sir.
with that?
But in normal conditions, sir.
Yeah.
In normal conditions, system A and system B, they will work at same time, sir.
Yes.
And only when one is failure, then work another one, right, sir?
Yeah. So they're both working together at the same time, quite happily. But if I lose system A, yeah, system B will carry on and move the control surface. So I've still got control of the aircraft. Even though I've got one hydraulic system failed, I can still fly the aeroplane because the other system is operating the controls.
Okay, sir. Got it, sir.
Okay.
Okay, sir.
Okay. Right. If nobody else has got any questions, then we will have a cup of tea there. It's 10:30 over here, so 10:50 my time. 20 minutes for a cup of tea, and then we'll plod on. Okay with that? Everybody okay? Cup of tea? 20 minutes.
Okay.
All right. Right, and guys, we got everybody back. Everybody there? One response. Thank you, Yadav.
Okay.
Right, lovely. Got everybody back. Then we'll plod on. Before I do, has anybody got any questions at all on powered controls? Nope. Okay then. We talked about feel earlier, yeah, and we said that the pilot needs to have some sort of feel. He needs to feel the aerodynamic resistance to the movement of his controls, so he knows how much input is going to result in how much output. Yeah, so with the manual controls, as it says in the notes, fixed proportion of the force exerted by the control surface felt by the pilot. With our power operated controls, he doesn't get that. Yeah, so experienced pilot knows a certain force applied to controls, certain rate of movement will be achieved. The force that he's applying and the force that he's feeling back will depend on the speed of the aeroplane, the density of the air around him, and how much deflection of the control surface he's getting. Yeah. If power control units don't have a field device, the only force required to maneuver the aircraft felt at the controls is that force that we need to move the servo, which has got no bearing at all on what's happening with the aeroplane. Yeah. So what we need to do, we need to introduce artificial feel. So when the pilot's moving the controls, he's going to get that resistance to his movement felt back through the stick. So he's not going to over-maneuver the aircraft. He's not going to over-stress the aeroplane. So you can imagine something this size, yeah, trying to maneuver that. Let's just say with the elevators, for example, for argument's sake, little pilot, he's going to be tiny in there. He's just physically not going to have the strength, the ability to move the control surfaces. Yeah, so hydraulic power is going to do that for him, and the only thing that the pilot's moving is the servo in the actuator. Yeah. The resistance to that movement, because it's all hydraulic, he'd have no resistance to his movement. He wouldn't know how much input he's getting at the control surface, so he could quite easily over-maneuver the aeroplane, overstress the aeroplane, do an awful lot of damage. So if we can simulate the resistance that he'd get when he's moving the controls by putting artificial feel in, then we're safeguarding him, safeguarding the aeroplane. And as it says there in the notes, yeah, the faster he's going to go, we need to take that into account. The density of the air where he's operating, we need to take that into account. And it says the deflection of the control surface, actually how much input we're going to need to move the aeroplane. Yeah, so that opposing force that we're going to put in, that resistance to his movement is our feel, and on a large aircraft with power operated controls, we're going to have to do that artificially. Ta-da! Right. Yeah, so the easiest and simplest form of feel that we can achieve is just by using a spring. Yeah, so somewhere in there, make a note that I'm not sure whether it says it, but the spring is the simplest form of feel that we can get. If I move the stick forwards or backwards, yeah, at the same time as I'm moving the servo valve, I'm compressing a spring. So if I move the stick back, I'm moving the servo valve, but I'm compressing a spring as well. So the further back I try to go, the more resistance I'm getting. And likewise on the forward stroke, push the stick forward, I'm moving the servo valve, but the more I try and do it, the more I'm compressing a spring, the more resistance is being felt against me. So that is a tidy, simple spring feel unit. Yeah. The disadvantage of that is it only gives feel for the controls for how much we're moving the control surface. It doesn't take into account the height of the aircraft or the speed of the aircraft. Yeah. So spring unit, the simplest form, but again, bottom of page, whatever we're on, 84, yeah, doesn't take any account of density or speed. Yeah. Only controls proportionately to our control surface deflection. So what we need to do is to bring in some sort of device that will simulate not only the control surface deflection, but it'll simulate the density of the air around us and the speed at which we're traveling. Yeah, and that piece of equipment is known as the Q-pot. Yeah, so the basic Q-pot, based on pressure difference across a diaphragm using pitot and static pressure. Obviously, static pressure is going to reflect the altitude and the density of the air. Pitot pressure, the dynamic pressure, how fast we're going. Yeah, we're going to put the feel unit between the cockpit controls and the servo. If the dynamic pressure increases due to forward speed, the force required to move the controls increases. And because we're getting that resistance, that's giving us more feel. If due to a decrease in air density, yeah, altitude increases, pressure difference across the diaphragm decreases, so the load on the column decreases proportionately. So what we've got is just a simple pot with a static pressure input on one side of a diaphragm and a pitot input on the other side of a diaphragm. Yeah, that's my control cables off to the flying control that I'm going to move, and as I move the flying controls, at the same time via a little sprocket, I'm moving a chain wheel, yeah, a sprocket. Yeah, as I move that sprocket, it doesn't matter which way I'm moving the controls. As I'm moving the sprocket, I'm acting on a push-pull rod, and that push-pull rod is acting against pitot pressure. Yeah, so as I'm acting against pitot pressure, the faster I'm going, the more pitot pressure I've got. Yeah, the harder it's going to be for me to move the controls. Yeah, I'm going to get that resistance to my movement. Likewise with the static pressure acting on the other side, and depending on how much static pressure you've got, again depends on how much assistance you get into the to move the controls. Yeah, so just again to run through. Yeah, the Q-pot, a cylinder fixed to the aircraft structure. In there, flexible diaphragm attached to a control mechanism by a rod. Diaphragm separates pitot and static pressure. Units designed so when the cockpit controls moved in either direction, the rod and the diaphragm are always deflected against pitot pressure. Worth a highlighter. Yeah, and that's page 85. Yeah, so with your simple Q-pot, whenever the cockpit controls moved, whichever way you're going, you're always going against pitot pressure. Yeah, and the load on the controls is released. Unit will always center due to the over-centering of the mechanism and the opposing force on the diaphragm. Yeah, so take your hands off, the thing will go to neutral. Controls operated, endless chain between the upper and lower sprockets rotates, moves the rod over center, pulls the rod against pitot pressure, return the controls to neutral, the diaphragm and the rod centralize the linkage. Force required by the pilot to displace the diaphragm varies with speed and density. Yeah. Everybody okay with that? Simple Q-pot. Yeah, so please remember the Q-pot, what it's there for. Yeah, remember that it's always acting against pitot pressure. Yeah, and that your simple Q-pot is going to give us feel for your movement, your altitude, and your speed.
Jim,
Simple enough thing. Yeah.
can you explain once?
You want me to go through it again?
Yeah.
Yeah, right. The Q-pot. Yeah, it takes in static pressure to tell us what altitude we're at. Yeah. So the higher up we go, the less pressure you're going to get in there. And it takes in pitot pressure, and pitot pressure is going to tell us how fast we're going. This setup here is our control cables to the flying controls. Yeah. So your flying controls, all you're going to be doing is moving the servo, the actuator. So what we need to do is to simulate the resistance of the air loads against the movement of the control surface. Yeah, so as I'm moving the control cables, which are going to move this servo, at the same time, I'm going to rotate a sprocket. And that sprocket via a chain is connected to a smaller sprocket. So if I move the, let's say I move the controls that way, yeah. So moving the controls that way, the top sprocket, if I move that way, that's gonna push that way, gonna pull that way. If I'm pulling that way, that's gonna go down. So the top sprocket is gonna turn in that direction. And as it does, it's pulling on this rod, yeah. As I'm pulling against the rod, I am pulling against pitot pressure. So the faster I'm going, the more resistance, the more force I've got to use to overcome that pitot pressure. So the more resistance I'm getting to my movement of the control column. Yeah. I've also got static pressure in there, and the static pressure is going to reflect the altitude that the aircraft's at. Yeah. If I take my hands off, everything's going to spring back to a neutral position. Yeah, the pitot pressure will go back to its neutral position, which in turn will pull this back to its neutral position, and the control cables will go back to the neutral position. You okay with that?
Jim, then if what happens if this diaphragm is worn out or is leaking?
I knew that was coming because somebody's got questions there, haven't they? So you tell me, what do you think would happen if that
Resistance will
diaphragm
be very
leaked?
Its resistance is very low, and the feel is less.
Yeah. So what's going to happen?
No feel.
Yeah. If that diaphragm's split, yeah, you're going to get pitot pressure and static pressure. The whole pressure just equalize out in the pot, wouldn't it? Yeah.
Yeah.
So as you're moving that rod backwards and forwards, yeah, you're not going to get any appreciable change. It doesn't matter what input you put. you're not going to get any increase in resistance.
That means fill.
Yeah. You with me? So your pitot pressure, yeah, it doesn't matter what you're flying at, your pitot pressures, if that diaphragm's leaking, you're just going to fill the whole thing with pitot pressure because the pitot pressure is higher than the static. Yeah, so there's no increase in resistance as you move in the flying controls, so you'd lose your feel. You with me there?
Yeah, Jim.
Hello, Jim.
Yeah.
Can you again please explain how this is only acting to Q side, to pitot side?
What, on the push-pull rod?
Okay.
That flying control, yeah, the control cable, as that control cable's going backwards or forwards,
Okay.
it's attached to, if you can imagine, that's my pulley, yeah, that's me. Control cables going around it. On the side, there's a sprocket, and that sprocket is attached by a chain to. That's meant to be a chain. It's not very good, but that's attached to a sprocket on the smaller pulley. So, looking at this side on, yeah, that's what you've got. This smaller sprocket, yeah, is attached by the rod to the Q port. Yeah. Not drawn very well, but you get the idea. Yeah. Okay. So if I move the wheel one way or the other, that chain, yeah. So let's say I move the control cable that way.
Okay.
Yeah. As I move that way, it's going to cause the chain to pull down. Yeah.
Okay.
So that's going to go that way, which in turn is going to bring that way. So as I'm pulling now, yeah, I'm pulling the rod that way. If I went the other way,
okay. Yes.
If I went that way, yeah, and I'd go up that way. No, I wouldn't. I'd be going the other way, wouldn't I?
Yes.
Yeah. So if that was going that way, and we said that's going to pull down. Yeah. If I went the other way, yeah. If I went that way, it's going to pull the thing up. Yeah. So that sprocket would go that way, and as the sprocket goes that way, it's going to pull the rod in that direction. Yeah?
Yes, Jim, I got it.
Okay, that's a good thing. Anybody else?
Jim, this diaphragm leak means the whole case leak is the same condition. Does it affect the same whole case and the diaphragm only?
No, if the diaphragm failed,
it's ruptured, let's say.
Yeah. So pitot pressure is always going to be higher than static pressure, isn't it?
Yeah.
Yeah. So if your diaphragm failed, then all your pitot pressure is just going to leak into this side of the pot. So you'd have an even pressure either side of the diaphragm. So it didn't matter what you did with the rod. Yeah, you've just got an equal pressure. So you'd get a bit of resistance, but nothing dramatic. Yeah, you're not acting purely against pitot pressure, because everything in the chamber's even Stevens. With me?
Okay, Jim. So want to know that this diaphragm leak or the whole case, pitot and
Well,
static.
if the whole case was leaking, you'd have no pressure in there at all,
Yeah,
because everything would just go in and come out again.
and has the same effect, right, as diaphragm leak.
Yeah, yeah. Again, if you didn't have any pressure in there, you'd have no feel whatsoever.
Yeah.
Yeah. If that thing's full of pitot pressure, you're just going to get feel, very limited feel, because you're not acting against anything. Yeah, because the diaphragm's leaking. Every time you try to move the diaphragm, your pressure's just going from one side to the other. So again, you'd end up with no feel. You'd just be moving the control surface.
Okay, then. Thank you.
You with me?
Yeah, thank you.
That's always a favourite one. Everybody has that question because it's come up, and it's the one everybody seems to remember for some reason. Right. Small, simple field pot. Absolutely tickety-boo. Yeah, and we're going to be acting against pitot pressure. Wonderful. But if we get a really big aeroplane, yeah, the larger the aircraft, the more feel that we need to provide, then that Q pot is going to have to become larger and larger and larger. And again, it could become so big it's just unwieldy and not worth it. So what we can do is use hydraulic pressure to help us with our feel. Yeah. So putting a Q pot in, what we're going to do with that, we're still going to use pitot and static pressure, but we're also going to use hydraulic power. Yeah. So the load felt in the control ram supplied by the hydraulic power, and the unit itself, the field unit, can be made smaller. See if we can find the thing for that. Yeah. Yeah, so that was the basic Q pot. If we're going into the notes, it talks about a bell crank lever neutral in the Q field actuator, and it's applying a horizontal force on the upper arm. As the controls move from the neutral position, the moment on the upper arm increases, moment on the lower arm decreases. Yeah. So all that's basically saying is that the more we try to move the thing, the greater the force we need to apply to move the control surfaces as well. Yeah, it's just a little bell crank that's in there as we move the control surface. Yeah. Control moved away from the neutral position. Moment on this little bell crank arm increases. Moment on the lower arm decreases, and that gives us increased resistance to the movement. We'll come across that in a ickle while. And there's our bell crank. Yeah. The bell crank, as I'm moving the control column, because of the setup, the more I'm trying to move it, the more resistance I'm getting to my movement. The other thing in here, and it's not a particularly fantastic drawing, I must admit, is the hydraulic feel unit. I sort of go through the text. When with power flying control actuators used in an artificial system must be prevented to prevent over control. Well, we've said all that. Spring force, simple spring pot normally adequate for the ailerons. Elevator and rudder normally have a spring and a hydraulic resistance as well. So the picture we've got shows a typical artificial field system using. No, it doesn't. Pardon me. Yeah, we can use spring units, and we can double up, and we can use hydraulic units as well. With this one, yeah, what we're doing, we're putting a pitot-static feed into a Q-pot and an actuator, and it's the movement of the bellows rather than direct movement of the control column affecting a diaphragm. What's happening there? The pitot-static pressure is allowing a feed of hydraulic pressure through to an actuator, to a little Q-pot type thing, the Q-field actuator. Yeah, so you got your simulator, yeah, using your pitot-statics. The faster we're going, the higher up we are, yeah, and that's going to regulate how much hydraulic pressure is allowed through the simulator down to the actuator. Yeah, the more pressure we've got, yeah, the harder it's going to be to move our piston. So we're flying along. Yeah, we put an input into the control column. That's going to move the servo. At the same time, yeah, we're now pulling or pushing. Sorry, we're now pulling against hydraulic pressure, and the more we pull, the harder it's going to be. And that bell crank that we were talking about, because of the way the moments are set up, it doesn't matter which way I'm moving, whether I'm going forward or backwards on the stick, the bell crank is going to cause me to pull against hydraulic pressure. So the more I try to maneuver, the more I'm pulling against that hydraulic pressure. As I release the stick, yeah, this is going to go back to its neutral position, and the back end of the actuator's open to return. Yeah, so it's the pitot-statics that's allowing hydraulic pressure to go through to the little Q-pot Q-field actuator. Yeah, and it's how much pressure is in there that we're acting against as we move the control unit. Is your basic premise for the hydraulic simulator. Yeah, so just showing how your control arm, just the setup of the bell crank, don't matter which way you're going. Yeah, don't matter which way you're going, you're still going to be pulling against the actuator, and the further you pull, the harder it becomes. Everybody okay with that? Yeah, lovely. Right, hydraulic field simulator. Yeah, spring unit in there. Control column. Yeah, inputs from the control column to, in this case, it's the elevator PCU. Yeah. As we move this quadrant, obviously that little off take there is going to the servo valve, and now we've got this little cam set up. Yeah, we've got a spring unit and a hydraulic unit, and this little, for want of a better word, it's a cam. Yeah, the more I pull the stick, the more I try to maneuver the stick. Now I'm acting against hydraulic pressure in the Q-pot. Yeah, and again, the more I move, I'm going to start compressing this spring, which again is going to give me resistance. So what's happening here? Yeah, artificial spring field, adequate at low speeds. At higher speeds, greater resistance to control movements needed to prevent overstressing the aeroplane. Artificial field systems return the controls to a neutral position when you release the control wheel or the rudder pedals. Elevator neutral is position where the elevators are fed with the horizontal stabilizer. So everything in alignment, that's the neutral position. The double cam on the elevator control quadrant shows how the field system places the control column and the elevators in neutral. Yeah, so that little cam, so as soon as we let go, that cam is going to ride around to the neutral position, and the spring and the hydraulic actuators will go there as well. Hydraulic pressure on the hydraulic field piston is varied with airspeed, and the horizontal stabilizer position, we'll come to that in a minute. Pitot pressure sent to one half of diaphragm, static pressure to the other half of the diaphragm. Diaphragm exerts a force proportional to the aircraft's speed. Force exerted against the spring on top of the stabilizer position cam, and the spring moves the metering valve. Yeah, so there's your metering valve. Yeah, little spring cap there. The more we move, yeah, the more that needle valve is going to shift. Hydraulic pressure coming in from the main supply. Yeah, and again, depending on how fast we're going, the pressure that's acting against the metering valve. Yeah, meter pressure forces above and below the metering valve equal, balance each other. Meter pressure acting against the relief valve balances the force on the spring acting downwards. Yep. Airspeed increases, downward force on the metering valve increases, overcomes the metered pressure force, pushes the metering valve down, opens the interior of the metering valve to the supply pressure line. Yeah, so the faster we're going, yeah, pitot pressure pushing down, that in turn's pushing down on this linkage, which in turn pushes down on the metering valve. As it pushes down, it's allowing hydraulic pressure to go into the ram. Yeah. So a pilot moves the control column, the field piston moves into the cylinder. So to be able to move it, yeah, we've got to be able to overcome that metered pressure. Yeah. So the more pressure it we're allowing in from the hydraulic system, the harder it's going to be to lift. Yeah. The more resistance I put in, yeah, then I can lift against that spring back to return. The slower I go, the more that valve closes off and reduces the amount of hydraulic pressure that I've got to work against. Yeah, so that the resistance will decrease. Yeah, so in the transonic region, shockwaves forming on the stabilizer cause the airflow of the elevators to become turbulent. Elevators become less effective. Subsonic speeds, certain force applied to controls would cause the aircraft to maneuver at a greater rate than if the same force was applied at transonic speeds. So to give the aircraft uniform characteristics, we allow the elevators to move further for a given load at transonic speeds. Which is done through this little gubbins here. Yeah. Not that we need to know that. We just need to be aware that the force the pilot has to apply to the field piston decreases at high Mach numbers. Tailplane incidence decreases. So that little thing kicks over, and it just alters the pressure that we've got to, or the position of the metering valve here to regulate the pressure that we're working against. Anything else? Sorry, I'm just going through the notes there just to make sure that there's nothing we need to worry about exam-wise. The advantage of the hydraulic pot, yeah, it reduces the size of the pot that we need. We're replacing huge amounts of pitot-static pressure. We're just using pitot-statics to operate a hydraulic valve. That hydraulic valve allowing a certain amount of hydraulic pressure into the actuator. So now, if I want to move the elevators, yeah, I've got to overcome that pressure. So I'll lift that little valve and I'll allow it off to return. The more I'm going, the faster I'm flying. The more the diaphragm's deflecting, the more pressure is being put down on the metering valve. Yeah, more pressure on the metering valve is allowing more hydraulic pressure to flow through, so that it's making it harder for me to move the controls. It's increasing the resistance. Does that make sense to everybody? Are we okay with that?
Hello, Jim.
Yeah.
And what is that connection for? That stabilizer connecting to that stabilizer, blue color, connecting to
That one?
above.
That's the horizontal stabilizer. That's the elevators at the back.
Okay.
When we go up into the transonic range, yeah, we're going to have a variable incidence stabilizer, so that the position of the whole stabilizer is going to move. Yeah. Okay. So we need to allow for that, and that's what's happening there. As we're flying faster, as we trim the horizontal stabilizer, again, this little cam mechanism is just repositioning the diaphragm, and it just makes sure that we get a uniform amount of feel. Yeah, no matter what speed we're traveling at. Yeah, we're getting the same sort of feel for the deflection.
Okay.
Yeah. Anybody else got any questions there? Yeah. Low speeds, we said we can use the spring. Yeah. And again, as the spring compresses, the further I compress it, the harder it's going to be. If I take my hands off, yeah, hydraulic pressure, spring pressure are going to cause this thing to go straight to a neutral position. Yeah, it'll all go neutral. However, yeah. We said with the manually controlled aircraft, or if we've got power assisted controls, yeah, we can correct for a flying fault by using trim tabs. Yeah. With our fully powered flying controls, a trim tab is totally ineffective, because the tab alters the position of the control surface aerodynamically. Yeah. So with your larger aircraft with your powered operated flying controls, that trim tab would have no effect whatsoever. Yeah, it's not going to, because we said we don't want any outside influences. When the control surface is in position, it's staying there. Yeah, so trim tab would serve no purpose. So the only means of trimming the aeroplane, yeah, of altering the control surface position, is by repositioning the servo valve on the actuator. Yeah, so to allow us to trim a power control system, the neutral setting of the actuator, the flying control unit, has got to be repositioned, and that'll move the control surface to trim the aeroplane. So your trim control, normally carried out using electrical or mechanical actuators. Actuator repositions the spring feel unit. Yeah, and when the actuator is operated using a trim wheel or a switch in the cockpit, spring wheel, feel unit, and the PFC servo are now repositioned to move the control surface and trim the aeroplane. So that the servo valve, the control surface, and the control stick have now got new neutral positions, And that repositioning is often known as control surface bias. And somebody asked about that the other day. Yeah, so it's when we're trimming a power operated system. Yeah, we're going to trim the actuator, select the control surface where we need it to be, and then we're going to reposition the spring field unit so everything moves to a new neutral position. Yeah. After trimming is carried out, yeah, it's essential that both the spring field and the Q field units are in the no load condition when the controls are not being operated. So by repositioning the neutral, yeah, we're repositioning the control surface, but we're also putting the field system into a new neutral. And that means as we move the control surfaces, we're getting that gradual resistance rather than meeting immediate resistance. Yeah, so trimming the aeroplane. Yeah, what we're going to do is put a trim actuator in the system. Yeah, so with our controls, yeah, going to the actuator. Yeah, we've got our spring strut, yeah, and then to move it, we can stick an actuator in, and by repositioning the actuator, we can reposition the spring strut, which will give us a new neutral. Yeah. Just going through it, the aircraft's out of trim. The pilot applies the controls to make the aircraft fly straight and level. The trim's then applied, the trim actuator extends and returns the spring field and the Q field units to their neutral positions. That removes the force that the pilot was applying prior to trimming, and now he can fly hands off and the aircraft will carry on straight and level. So we're jogging along, yeah, sticks in neutral, the trim actuator's in neutral, the pitot or the Q pot is in neutral, and the control surface is in neutral. So everything happy. Yeah, pilot needs to trim the aeroplane, so he moves the control surface to maintain straight and level flight, and he holds that control column in the required position against control force supplied by the deflected field unit in the bellows and the spring unit. So he's moved the stick forward. Yeah, that in turn has via the linkage, the trim actuator pulled on the belt crank. Yeah, which in turn has moved the Q pot. So now he's moved the control surface. He's got the resistance that he needs because of the Q pot. Yep. So now what he's going to do is trim. He's going to move the trim actuator, and by moving the trim actuator, he's resetting the neutral, moves the belt crank, and in doing so, yeah, the neutral is now adjusted on the Q pot as well. So pilot selects a trim switch, the actuator extends to reset the field unit bellows and the spring unit to neutral. Control surface remains in the required position, and the force that the pilot had been applying has been removed. Yeah, so by extending the actuator, yeah, extend the actuator, we're resetting the linkage. So now we've got a new neutral for the field unit. So now if I want to move the control, I'm starting from that new neutral position, and my resistance to movement will build up gradually. And that's basically what our powered trimming is about. Nothing else we need to say there. Is everybody okay with that? In fact, the picture in the notes is actually a little bit clearer than the coloured in one on the slide. Just shows how the bell crank is repositioned. So your bell crank's starting at 90 degrees, yeah, should we say. As we move the control surface, yeah, via the bell crank is moved, and then by extending the actuator, we're going to put the bell crank back to its original position. By doing that, we are resetting the neutral position on the Q field unit. Anybody got any questions, queries, problems there? That was artificial feel. Yeah, so fail-safe features then in our hydraulic system. Yeah, aircraft fitted with power flying controls. We said that there's always a possibility of failure of the system. And if the system fails, then there's a potential to lose the aeroplane. Due to the forces required to operate the controls in manual, not being achievable because the crew are weak, even the Hulk would struggle. Yeah, so if we get a failure, we still need to maintain control of the aeroplane. So the methods that we can use for that, 2 or 3 complete hydraulic systems can be used to operate the power controls. And additionally, we can provide backup systems. Main hydraulic systems work together continuously, but each one is self-contained. Yeah, so if one system should fail, the remaining systems will provide power for all the normal manoeuvres and what have you required to complete the flight and get us back down to Earth. Additional backup, as we saw before, we can get electrically driven pumps, air turbine generator, or an air-driven pump. So what else can we have? Yeah, we looked at tandem actuators, and we said for our control surfaces, yeah, we could put a tandem actuator in, where we've got 2 separate hydraulic systems feeding into the same body, but in that same body there's 2 separate setups with servo valves and the rams and what have you, 2 lots of hydraulics. So if I lose one side, the other will carry on working. I could split the control surface. Yeah, so I could have 2 control surfaces working together in tandem, completely in harmony. But if I lost one system, yeah, then the other system would carry on and allow me to control the aircraft. Same sort of affair, but I've got 2 actuators, 2 separate systems, just driving one complete control surface. Yeah, so one piece surface operated by 2 PCUs, independent hydraulics. We can split the control surface, give its own, each one its own independent control hydraulic system. Tandem actuators, we've been through those, mentioned those. It says in the notes, some aircraft can be flown at a reduced speed in manual condition, but they'd have to be fairly lightweight, again, as it says. Requirements with regard to primary flight controls and trimmings are set out in CS25. We've already mentioned that if a control system is jammed or there's a break in the control run, the aircraft has still got to be able to continue safe flight and landing as soon as possible. And that requirement met by duplicating. Yeah, and a good example of how we've duplicated and interconnected. Yeah, 3-engined aeroplane. Yeah, 1 engine, 2 engine, 3 engine. Each engine driving pumps, an engine-driven pump and an electrical pump, and each engine feeding into different controls. So your number 1 system, the red one, feeding into all the red bits. The number 2 system, the yellow system, feeding into the yellow bits. Yeah, if I had a failure on one of the pumps on number 2 engine, the other pump, normally the electric pump, would take over and run the system. Same on the number 3, but on the number 3 system, we've actually got a couple more additional auxiliary pumps there. Green system, again feeding into wherever it's green. System 1 and 3, yeah, interconnected by a power transfer unit or a reversible motor pump, as they're calling on here. We called it the PTU, the power transfer unit. So if I had a failure in the green system, yeah, I could get the red system via the PTU running the green system things. Likewise, between the yellow and the green, yeah, we've got a PTU there, reversible pump. So if I had a failure in the green system, the yellow system would take over. So 2 systems, yeah, running the ailerons, elevators. Yeah, again, the yellow and the green system running the elevators. So I've got 3 systems on the elevators. Yeah, and your various ailerons. Flying controls, yeah, the upper and the lower rudder. Yeah, so really interconnected hydraulic drives to all the systems, and with that backup on the backup on the backup. So eventually, if I lost 2 systems, I'd still have a third being able to power all the essential side of things. Yeah. So if I lost my yellow and my green system, the red system would still be driving the essential controls. If I lost the red system and the green system, the yellow system would be operating the essential controls. So there's always that backup available. Various little safety devices that we talked about previously, protecting the mechanical side of things. Again, just be aware you might not get all these different components in one system, but they're all lumped together just to show you what is there and thereabouts. The disconnect mechanisms that we looked at, this is shown as an elevator system. Yeah, so we've got a disconnect mechanism. So if we've got a jam on one side, yeah, can't move it, we can, or a severance even, we can disconnect one side from the other. The duplication, both running down either side of the fuselage. Disconnect mechanism at the back, should we get a problem at the rear end. Yeah, there's an automatic disconnect there that we, again, that dog clutch we looked at. The override springs, the crush struts, and the cable brake detectors, they're really good. Just a little spring fits between 2 cables. If one of the cables breaks, the spring's going to pull the 2 contacts together and put a light on in the cabin. So for your mechanical controls, cable brake detectors indicate a slack or a broken cable. Rotary damper provides to dampen feedback oscillations. So if we've got flutter or severe turbulence on the elevator, the damper would just damp it out a little bit for him. Override bungee permits continual movement of the serviceable control path should a jam occur in the opposite one. Pitch disconnect, yeah, allows 2 control columns to be disconnected from each other to allow independent motion in the event of a jam. And the aft disconnect, electrically operated device automatically disconnects the 2 paths should a servo valve or should a servo failure occur in either of the paths, any of the paths. Again, you get CWP warning lights if the things have been activated. And somewhere over the rainbow, yeah, that's our cable brake device. Yeah, it's just two little pulleys that sit on the control cables. If one of those cables becomes too slack or snaps or gets cut for any reason, let's say it chafes through, yeah, the spring's going to bring the two pulleys in contact. As they come towards each other, it makes a switch, and that'll put on a warning light in the cabin. Yeah, normally the two things held apart by the tension on the cables. If that tension becomes too loose, that spring's going to pull everything together. Ta-da! Anybody got any questions on that little lot? No. Right, what we'll do, we'll just have what's that? 10 to, yeah, we'll just have a quick 10-minute break. Stretch your legs, stretch your eyes. We'll have a look at the tailplane system, and then we'll stop for lunch. Okay?
Okay, Jim.
Okay. Right. I'll see you in 10 minutes. Won't take long to go through this lot. Okay, right. We'll plod on. Sanjay, you got your hand up. Was that a question or a button press? I'll assume a
I'm
button
ready to
press.
study now. We can ready. We can continue.
Yes, I was just saying to Sanjay, you got your hand up, so I wasn't sure why, whether you had a question, that was all. Okay, right, so the variable incidence tailplane. We talked about the need for the variable incidence tailplane when we did our theory of flight. Yeah, normal cruising flight. Yeah, the aircraft would have a tendency to try and fly nose down because the center of lift behind the center of gravity. So what we do, we put a downforce on the tailplane to bring the nose up. We could do that by moving the elevators, putting them up into the airflow, but that in time would cause an awful lot of drag, which means we'd have to provide more thrust, which means we use more fuel, which becomes very expensive, and it puts quite a strain on the elevator as well. So the way we can get around it is by adjusting the angle of incidence of the tailplane itself. Yeah. So rather than having the elevators up, if we just adjust the position of the whole tailplane, we can generate the same amount of downforce without the need for drag and all the rest of the good stuff. Yeah, and that's our variable incidence system. With the variable incidence system, yeah, we've still got the elevators, and we can still use the elevators for control. And if we're repositioning the tailplane, we've still got the full range of movement available to us. Yeah. So again, purely for info purposes, yeah, just showing how much lift you can gain, or the same amount of lift, yeah, by moving the angle of incidence and still keeping the elevators fed. The other way down, yeah, just move the angle of incidence down, keep the elevators fed, and we're still generating the same amount of lift. Large jet aircraft, yeah, longitudinal trim achieved by varying the angle of incidence of the horizontal stabilizer. We've said that. Operates in conjunction with the elevators, yeah. So by moving the angle of incidence of the tailplane, yeah, we'll keep the elevators fed. Gives us a much wider range of trim, yeah, more precise manoeuvring. It says because we've still got all the elevator range available to us. Also, the variable incidence tailplane, again, as we covered in theory of flight, overcomes the loss of effectiveness of the elevators at higher Mach numbers. Yeah, so how can we operate the thing? Yeah, page we're on 99. Yeah. We can operate the incidence of the stabilizer. Yeah, we can change that by any of 3 methods. Yeah, an electric actuator motor using 2 switches on the control columns. That is your trim switch. Yeah, please, on page 99. Yeah, remember we need it's on that first bullet point. We need 2 switches there, and the purpose of both switches is to prevent actuator runaway. Yeah, so we're going to have an armed switch and a command switch, and both those signals have got to be present before the trim motor will run. Yeah, we can use a trim servo motor operated by signals from the AFCS. Yeah, and if the AFCS isn't in operation, then the servo motor can be operated by the Mac trim system. And we can operate it by the manual trim wheels located in the cabin. Normally used for emergency if the other two fail, because it's going to be a hell of a journey trying to turn the trim wheel. Yeah. Where's my thing? Yeah. So your main motor actuator we mentioned, the servo motor in from the AFCS, and the cable input from the trim wheel in the cabin, all via a set of gears to an output rod that will drive a screw jack, and the screw jack going up and down, is going to alter the angle of incidence of the tailplane. So again, just running through what it's saying in the notes here, the actuator assembly consists of a screw jack, a threaded ball nut connected to the front of the horizontal stabilizer. The gimbal's just there to allow for angular movement. So as the tailplane's moving, the gimbal's just a posh name for something that's going to permit that angular movement. The ball nut and the stabilizer movement is limited by stop nuts at each end of the screw jack. Yeah, they are mechanical stops. Just prior to that, there are limit switches. The idea of the limit switch is to cut off the electrical supply when we get to the selected position. The stop nuts are there in case it all goes horribly, horribly wrong and the actuators run away and it prevents the stabilizer coming off the drive of the screw jack. Primary method of rotating the screw jack is by a 2-speed electric motor driving gears which form part of the actuator. Control column switches are operated together. Electric motor operates in one direction. Drive transmitted to the screw jack, and permits the screw jack to rotate. If I want to go the other way, the flip side happens. The motor rotates, drives the screw jack again via the clutches, and it can go in the other direction. The idea behind that is if we need to reverse the position of the screw jack, we can do it fairly quickly. Page 99 again, just from third paragraph up from the bottom. Normally, the trailing edge flap position determines the motor speed. Low speed when the flaps are retracted. When the flaps are not up, the motor operates at high speed. Okay with that? So the flaps up, the motor will revert to low speed operation. Take the flaps away from the up position, anywhere away from the up position, the motor will run at high speed. Again, stick your little coloured pens through that. Limit switches, as I said, prevent the ball nut being driven to either of the stop nuts. So the limit switch, similar to what we saw earlier on. Limit switch contacted by a striker on the stabilizer, it will de-energize the clutch. Should the actuator not be driven onto either of the stops, a mechanical torque limiter will prevent damage to the actuator. So if the thing drives past the limit switches, drives up to the stop nuts, if it's still rotating, it's going to meet a lot of resistance, and the torque limiter will sort of disconnect it, so it'll carry on rotating, but it's not under any load, so it's going to prevent any damage. So at least we've still got the ability to move the thing mechanically if necessary. Braking system, yeah, brake system prevents the air loads from rotating the screw jack when the trim system's not in use. So when the thing is in its selected position, yeah, there's a brake applied. I think it's a solenoid brake. Screw jack's rotated by the actuator. Yeah, when we make a selection, the brakes will release. Be a failure of the main actuator motor system or the automatic trim servo motor, then we've got a manual reversion from the cockpit on the trim wheel. Like I say, that's a bit of hard work for the pilot. The variable incidence tailplane screw jack operated by reversible hydraulic motors instead of an electrical motor. Like the electrically operated one, needs 2 signals to allow the motor to operate. Again, it's prevent that trim runaway. Yeah, if you had the trim runaway and this whole stabilizer goes to the fully up position, we could be in a whole world of hurt. Yeah. The trim switch is normally located on the hand wheel around about thumb position. Yeah, and again under one cover we've got the 2 switches. Yeah, so we've got the armed selection armed up and the command signal up. So if I want the thing to move up, I've got to make both of those switches, the armed and the command. And likewise, if I want a down selection, I've got to arm and command it down. Yeah, dual thumb switches, captain and first officer's control columns used to alter the angle of incidence of the stabilizer. Limit switches de-energize the armed and command solenoids should the stabilizer reach the limit of its travel. Happy days. Yeah, position indicator provides a continuous indication of stabilizer's trim. Yeah, we need to know where the trim is. So there's a trim indicator and a scale. It says on the control stand, calibrating your units of trim. There's an area outlined to indicate the proper range of stabilizer trim, and that's often referred to as the green range. I'll come back to that in just a minute. It's adjacent to the hand wheel. Let's just see if we get a picture of that. Yeah, when we're talking about the green range, just while it's there, yeah, we've got the stabilizer trim switches on the control wheel at the thumb position, sprung loaded to neutral, and we need both signals there for the up and the down, the command and the armed. Your manual override is a little winding wheel that's on the side of the center console. There's a little pop-out handle. Yeah, so we can pop the handle out and we can wind like buggery. Yeah, and that will adjust the position of the stabilizer. Next to that, yeah, is an indicator. So as that wheel turns, yeah, it's going to show how many units of trim we've got applied. There's normally a gauge on the console as well on the front that'll give us a similar information. But with this thing, when we adjust the trim, this wheel, because it's connected mechanically, will turn as well. Yeah. On the indicator gauge, how many units of trim we've got applied, there is what they call the green range. Yeah, and that green range is there to say that the stabilizer is in the correct position for takeoff. If you're outside that green band and you try and take off, it's going to go horribly wrong. So one of the checks that they've got to perform prior to takeoff is to make sure that the trim indicator is within the green range. Okay with that? Yeah. We'll come on to it. I think we'll hit it again, but make sure that you've run a highlighter through the green range, and that is to ensure that we're in the correct position for takeoff. Stabilizer in the correct trim position. The elevators provide control in pitch. Yes, so we've trimmed the stabilizer. We've still got elevator control, so we can control the elevators manually using the control column. They will move to remain with the stabilizer through what they call the neutral shift. The Mac trim system, yeah, again, the elevators will be moved by the Mac trim system and also by the AFCS, the automatic flying controls. So what we got, yeah, we have control column, yeah, we've got the trim switch on there, yeah, and we've got our fore and aft movement on the control column, yeah, via our control cables, yeah, up to the screw jack, yeah, and the screw jack, as we've seen, is going to rotate in and out, and that's going to drive the nose of the stabilizer up or down. Again, a bit of a confused drawing, but we'll get the idea. Attached to the back of the horizontal stabilizer are the elevators. Yeah, the elevators giving us our pitch control. And the elevators responding to inputs from the control column, yeah, via a cable quadrant and some push-pull rods. And as we move the control column, that's going to put an input into the PCU. Yeah, PCU moving the elevators up or down. Yeah, the elevators are also displaced by the neutral shift rod. The neutral shift rod is there to make sure that as the stabilizer is moved, the horizontal stabilizer is moved, or the tailplane is moved, then the elevators will remain in line with it. Yeah, so as the stabilizer moves, that neutral shift rod via a little bell crank, again, it is putting an input into the elevator PCU, the elevator actuator. So as the stabilizer is moving, the elevators are going to move to stay in line with the stabilizer. Yeah. That little graph that we saw earlier, wherever it's gone, does it come a bit further down? Yeah, little graph is showing the elevator movement as the stabilizer is trimmed. Yeah, control column inputs cause the elevator to move from that new neutral position, change the elevator neutral position, transmit it back through the control linkage to reposition the control column. Yeah, so the range of elevator neutral shift varies with the Mac trim actuator position. Again, we'll come to that. So for your neutral shift rod, yeah, that neutral shift rod is making sure that the elevators remain fed when we've moved the stabilizer. Yeah, shift rod transmits stabilizer movement to the servo valve of the PCU, and the PCU physically moves the elevator. And that means we've got the full range available to us should we need it. And then it goes on to talk about Mac trim. Yeah. Again, I'll go through this. The Mac trim side of things, with changes in airspeed, the pitch trim of the aircraft is also going to change. We said that previously. As airspeed increases, the aircraft will adopt a nose down attitude. Yeah, slower aircraft, we just trim the elevators to get around that. High-speed aircraft, though, are more affected by the changes, and the faster we go, those changes can occur quite rapidly. So with our high-speed aircraft, we use an automatic Mach trim system. Mach trim system has a Mach speed sensor in the air data computer, an amplifier and a servo motor, sensor in the ADC supplied with pitot static pressures. Transducer produces a signal that's amplified, drives a servo motor or an actuator. In the system that shows us in the notes, the Mach trim actuator is part of the neutral shift mechanism. It functions as part of that neutral shift mechanism, except when the Mach trim is operating. The Mach trim needs to operate fairly quickly. Yeah, so at speeds below, it says 0.7 Mach here, the Mach trim actuator is fully extended. As speed increases, actuator retracts, rotates the trim centering and feel unit and through the aft quadrant and linkages, the servo, the PCU, causes the PCU to move down, so the elevators move up, and the tailplane automatically repositions to fare with the tailplane. So what's happening there? We've got the neutral shift rod, and attached to that is the Mach trim actuator. Yeah, below normal speeds, if we move the stabilizer, the PCU, the elevator reposition. Above a certain speed, the actuator extends and it rotates the centering unit, the field trim and centering unit round. So now, as we increase speed, yeah, the actuator rotates that, and through the F quadrant and linkages, causes the PCU to move down, so the elevators to move up. So the faster we start going, yeah, this thing rotates this little lot. Because this little lot is rotating, yeah, it's putting an input into the PCU, which is moving the elevators. Yeah, as the elevators are moving, the stabilizer will eventually catch up, and we'll go into that neutral position. Yeah, does everybody understand that? Okay. Yeah, the neutral shift mechanism. The neutral shift is there to keep the elevator fed with the horizontal stabilizer. At faster speeds, when we need to trim the aircraft very, very quickly because of the high speeds involved, yeah, that neutral shift rod, yeah, forms part of the Mach trim system. At higher speeds, the air data computer will send a signal to the Mach trim actuator. That actuator will move. It will turn the centering unit. As the centering unit turns, that is going to put an input into the PCU. Yeah, so the PCU will now move the elevator to trim the aircraft at high speeds. As it trims the elevator, again, because of the neutral rod, that's going to position the stabilizer, so they'll be fed together at the trim position. Tailplane automatically repositions to fare the elevator with the tailplane. Automatic flight control system engaged. Pilot's linkage to the PCU is locked in a central position. Yeah, movement of the elevators by command signal from the AFCS, carried out by sending a signal to the transfer valve that we looked at. Yeah, so the AFCS monitoring what's going on. Once the elevators to move, it will signal to the transfer valve. Transfer valve will do as required. Move the elevators, yeah. Again, till we reposition them. Again, if it's a long AFCS command, yeah, the AFCS will then reposition the tailplane to trim the aircraft longitudinally and bring the tailplane back in line with the elevators. If we've got an all-moving tailplane, the Mach trim actuator will move the the servo valve of the tailplane PCUs. So although that was a long-winded thing, fairly easy. Yeah. We've got trim inputs into the stabilizer, trim inputs into the elevators, and the elevators moved by the quadrant. Yeah. As we move the quadrant, that's in turn moving the PCU, which is moving the elevators. The neutral shift rod is there to keep the elevators and the stabilizer fed together. Yeah. Move the stabilizer. The neutral shift will put in an input into the PCU to move the elevators into the new neutral. Anything else happening there? We said the Mac trim actuator. As the Mac trim actuator moves, we want an input into the elevators to keep us trimmed, but that needs to be a quick reaction. So as that moves, yeah, again, it's putting an input into the actuator. If the autopilot shifts things, or the AFCS, again, it's designed. It'll move the elevators via a transfer valve. Yeah, if we're going to stay there for any length of time, then the AFCS will bring the stabilizer in line with the elevators. Please, as I say, remember the functions of the neutral shift rod on page, what did we say, 105, and I think it was 102 as well. Yeah, so stick your highlighter through the functions of the neutral shift rod that sometimes crops up. Yeah. The purpose of the variable incidence stabilizer, yeah, so we can have trimming on large high-speed aircraft. We don't need to worry too much about this little lot, but this is just showing the gearing that's in the drive for the screw jack. Yeah, motor putting an input in. The thing will run in two directions. Yeah, release mechanism. Yeah, so how it one side's going to disconnect from the other, and then there's the brake assembly in there as well. So when at the selected position, no input, then the brake will be applied. Once we get another input, then the brake will release. Anything else I need to say there? Not really. Stabilizer, yeah. Trim switches, I've already mentioned those. The trim handle, just this little pop-out lever that you grab hold of, and you turn the wheel, and by turning the hand wheel, that is going to move the screw jack, the horizontal stabilizer. Very important we know about the green range. Yeah, and that tells us that we're in limits for the trim for taking off with the aircraft, and the units of trim that we've got applied. So if you make a trim selection on the thumb wheel, yeah, that wheel will adjust to give us the relevant trim reading. The all-flying tailplane, the all-moving tailplane, yeah. Tailplane connected to the pilot's control column using cables, linkages, hydraulic actuator. It's hinged, the elevator's hinged to the trailing edge of the stabilizer, but the elevator is not under the control of the pilot, but it's positioned according to the movement of the stabilizer. Yeah, high speeds, the stabilizer provides more efficient pitch control than just the elevators. So the efficiency of the elevator is reduced, certainly when it's operating in the air behind the shockwave. Elevator is connected to the stabilizer by means of cables that pass around cable drums. Yeah, ends of the cables fixed to the fuselage structure. Stabilizer is moved. leading edge is moved up or down, the cable drum will move with the stabilizer. The cables pass around the drum. Movement has the effect of lengthening one cable, shortening the other, thereby moving the elevators in the required direction. So yeah, your forward cable drum mounted there in the nose, your hydraulic actuator moving the stabilizer. As we move the stabilizer via this cable arrangement, little quadrant as the stabilizer moves, the cable drum moves. It causes the quadrant to move, and as it does, it's going to deflect the stabilizer by the required amount, of the amount that's set up. And that, guys, I think is a pretty good place to stop and have lunch. I'll make that 12:25. What we got in Kathmandu? Right then, guys. Welcome back. Everybody fed and watered?
Yes, sir.
Happy?
Yeah.
And before I rattle on, has anybody got any questions at all from this morning's stuff? Any questions? Right, if that's the case, brilliant. Which means my teaching's perfect. So the next little bit that we go on to then, we've had a look at the tailplane, the variable incidence tailplane, and we've said that it's going to be moved by a screw jack, and that saves an awful lot of drag, which is going to save money. We've still got the elevators at the back, so we've got full control, full authority over the elevators. The tailplane driven by a screw jack. Different inputs for the screw jack from the trim wheel, from the trim buttons, from the autopilot, and from the Mac trim system. Pardon me. Don't forget about the neutral rod. Yeah, the neutral rod, keeping the elevators fed with the stabilizer during normal operation. And the neutral shift rod also works with the Mac trim system. So when large trim movements are, or when very, very quick, rapid trim movements are needed, the Mac trim system will move the trim centering quadrant. Yeah, that'll put the trim mechanism, trim input in. And then the neutral shift rod will be making sure that the tailplane comes to fare with the elevators at the end.
Excuse me, sir.
Yeah.
If you move the stabilizer, sir, is the cable will also move with the stabilizer, elevator cable?
No, it's all done as part of the mechanism.
So, but in page number 108, it's written like that.
Sorry, I can't hear you. Turn your mic up a bit or shout. Sorry, I couldn't hear you. You have to shout at me. Your microphone's switched off now.
At page 108, in second paragraph, just you read the from the last second paragraph.
What page?
108. The elevators are connected to the stabilizer by means of up and down cables and pass around the forward cable drum and rear quadrant. The ends of the cables are fixed to the freezer structure. When the stabilizer moves such that the leading edge moves either up or down, the cable drum also moves with the stabilizer.
Yeah, the one that we looked at before was the variable incidence tailplane. This is the all-moving tailplane. Yeah. So it's the tailplane itself that's under the control of the pilot. So it's not the variable incidence one. This is the all-moving tailplane. Yeah, and the all-moving tailplane, the elevators are just connected to the tailplane. So when I move the tailplane from the by the control column, yeah, I'm moving the actuator, and it's as the tailplane moves that the elevators will move. The elevators aren't in contact with the pilot at all.
So, but the stabilizer will move with the control switch, no?
The stabilizer will move, yeah.
When the
The whole
stabilizer will move,
the whole
cable-
stabilizer will move, but as the
Yes.
stabilizer moves, the elevators will move at the same time. The elevators are being moved by it's just two cables wound around a
Yeah.
drum inside, and the elevator is connected to the stabilizer by a rod. Yeah, so as the elevator moves, as the pilot moves the stabilizer moves, sorry, as the pilot moves the stabilizer by the actuator, yeah, then the elevators will move automatically with the stabilizer.
Okay, thank you.
You okay with that?
Yes, sir.
Lovely. Anybody else got anything? Right, so what we'll look at now then is the ailerons. Yeah, and the ailerons, as we've seen, are used for roll control. Yeah. The notes are just showing a typical system, as it says. Yeah, roll control for most large jet aircraft, provided by the ailerons, operating in conjunction with the flight spoilers. Yeah. Ailerons will control at high speed. Yeah, they're quite good for high speed. But the first few degrees of aileron movement occurs without differential movement of the spoilers. Yeah, so at high speed, we'll just use the ailerons. As we slow down, we can use the spoilers with them. And the fact that the ailerons move before the spoilers do allows us to trim the ailerons. The control wheels, yeah, have an aileron trim indicator, yeah, and an autopilot disconnect switch. So that when it's talking about the control wheels, we're talking about the hand wheels. Yeah, where we'll have a trim indicator somewhere, and on the back of the wheels there's an autopilot disconnect. Trim switch is normally mounted on the center console, and there's an aileron position indicator somewhere on the pilot's panel as well. The typical system, we've normally got two power control actuators provided for each aileron, attached to the rear wing spar with the rams attached to the aileron. Yeah, aircraft has, it says normally, the example given, the aircraft will have 3 independent hydraulic systems to operate the ailerons, elevators, rudder, spoilers. Normally we just use 2 systems to operate the aileron PCUs. Systems are independent of each other, as we looked at previously. And if we lose one system, the other will take over. Each power control unit, it says, is monitored for failure. Things like stuck servo valve. If we do get a failure in the system, then we'll get a warning sign in the cabin. Control achieved through cable and pulley system up to the actuators, and the wee safety features that we talked about previously. The 2 hand wheels linked by the cables and the interconnecting shaft. Disconnect mechanism in that shaft, so if we get a jam or a severance, we can disconnect the 2 systems. Yeah. Artificial feel in the system that we're looking at is going to be provided by a spring. Yeah. And both ailerons have PCU, each PCU dual unit, 2 equal and parallel power components, trimmed by a little trim motor. Yeah, so what they're showing, the hand wheels, yeah, we talked about the disconnect device. Through your quadrants, through your cables, trim actuator input, similar to what we saw the other day. Autopilot input, again, we saw autopilot inputs. The Springfield unit, we'll look at that in a bit more detail. From there out to the PCUs. Yeah, 2 PCUs. If you get a failure in one system, the other one will still carry on operating the aileron. And also shown, which we'll describe later, is an aileron flutter damper. And that is there just if we get a failure in any of the linkages, it's going to prevent the ailerons from fluttering. Yeah. PCU, same as we've seen before. Yeah, just servo actuator, and that's going to move the ailerons up and down. So let's see where we're going from there. Yeah, so there's a lot of writing. Yeah, it says the hand wheel assembly mounted on top of the control column. And I'm just going to read through this to make sure that there's nothing that we need to highlight. Yeah. 2 stops are fitted, limiting the travel of the hand wheel, left and right. Hand wheel got your pitch trim switches, your autopilot disconnect, and it'll have a radio press to transmit switch on the back of the stick as well. Disconnect mechanism uses a dog clutch to keep 2 halves of the thing. Take the locking pin out, the 2 systems disconnect. So that's similar to the one that we saw the other day, but the one that it described was in the elevator system. So this one's got the same sort of thing, but it's just in the aileron system. Yeah, but it's exactly the same principle, same component. 2 halves of the connecting shaft have been disconnected. Only the unjammed aileron circuit can operate, which is fine, which is what we want. Quadrants, just attach the cables to the quadrant, and that allows it to operate. What else do we need to see? Yeah, just example of your quadrant, and then the inputs from the wheel are transmitted down to the ailerons. 2 run either side. Rear quadrant. The rear quadrant receives inputs from the trim mechanism. Where's the trim actuator? There's your rear quadrant. Yeah, you've got a trim input in there. Artificial feel unit, spring-loaded roller. Yeah, we'll look at that in just a moment. And the right-hand quadrant takes in an input from the autopilot as well. Cable tension regulator, needn't worry about those. We know what those are for, just to make sure that the cable tensions are maintained throughout. The PCU, we've talked about PCUs. And in this case, it's in the 2 identical parallel working balanced actuators. So we've got 2 actuators. 1 control surface, position transmitter located on the rear spar of the wing, linked to the aileron. Position indicator provides indication of your movement of your aileron. Each aileron equipped with a flutter damper, a little double acting actuator attached to the rear spar of the wing and connected to the aileron front spar by an idle lever breakaway link. Right at the bottom there, page 112, stick your highlighter through the fact that the purpose of the damper is to prevent aileron flutter should both PCUs fail. Yeah, there's a little link. Yeah, we'll disconnect the damper should, or it prevents the aileron jamming should the damper seize for whatever reason. Yeah, so there's a little breakout link on there, but please stick your highlighter through the purpose of the damper. Prevent flutter should the actuators fail. And then we'll get a nice picture of what we've been talking about. Rotation of the control wheel rotates the quadrant mounted on top of the control column. Circuit then routed down and out of the control column. Circuit ends at the forward quadrant. Cable run goes from the forward aileron quadrant to the aft aileron quadrant. Routed along either side of the fuselage, so any damage to the fuselage is unlikely to affect both of the cable runs. Aft quadrant, yeah, control centering, artificial field, trim input, autopilot input. We've kind of looked at those. Fill unit forms part of the aft quadrant, consists of a spring-loaded roller held in the centering detent. We shall look at that now this minute. Yeah, and that is your fill unit. Yeah, fill unit forms part of the aft quadrant. Yeah, has a spring-loaded roller. Yeah, so you got a spring lever, a little roller. The more I pull on the cable, the more I'm pulling on that fill spring, the more resistance I'm going to get to my movement. And when I take my hands off, because of the cam shape, the roller is going to drop back into the center. Yeah. So control input made, spring-loaded roller moves out of the centering detent, rides up the cam, stretches the spring and provides that feel. Control wheel input's relaxed. Spring pulls the roller back to the centering detent. From the aft quadrant, the cable run goes to the aileron quadrant and tension regulator, which in turn operates the PCUs. And again, we've got a left-hand interconnect shown. Trim actuator, yeah. So should we trim? We're just going to reposition. Yeah. Not a lot else to say there. Yeah. So that's it in reality. Yeah, we've got the trim actuator. Trim actuator is going to reposition the neutral if we apply any trim. Yeah, again via a little bell crank. Aft quadrant, left hand, the right hand, they're pretty much the same apart from the trim input. And don't forget with your ailerons, you only need to trim one side because the other's going to do the exact opposite. So if I trim the right hand aileron up a little bit, yeah, then the left hand wing's gonna drop because you've got that drag. So trim system, 2 switches, the armed and the control switch located on the center console, the trim actuator as we see. Yeah. The actuator will rotate the artificial field unit in the aft quadrant. Trim switches are operated. The actuator displaces the roller arm and roller. Detent keeps the roller centered in the cam profile. That rotates the control wheel and gives the actuators the signal to move to the selected position. So your trim actuator, driven by switches in the cockpit on the center console, and again we'll have a trim indicator. So your trim switches, yeah, 2 switches, left and right, sprung load to center. Ta-da, 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 ta-da. Right. Let me see if I got my little sketch. Yeah. Right, your ailerons. Yeah, it was said before, and we'll just have a look again, that one of the problems at high speed that we get with ailerons is a twisting of the wing. Yeah. If I'm going at high speed and I try to put the aileron down, the air loads push up on that aileron. Yeah, they try to push it back up because we're going that fast. And at towards the tip of the wing, where the structure's quite weak, what can happen is it can actually twist the wing. So as the wingtip at the outer end, well, as the wingtip starts to twist, yeah, we're changing the angle of attack. So rather than the wing going up like you'd expect, because you've changed that angle of attack, that wing can drop. And that phenomenon is often called control reversal. And it's not the fact that the controls are reversing, it's the fact that the aerofoil is actually twisting. Yeah. So again, if we try to put the aileron up, yeah, one's going down, the other's going up. The upgoing aileron, yeah, the airflow is going to try to push it down, so again the wingtip twists. So you got one twisting down the way, the other twisting up the way, and it can create all sorts of problems. Well, it did when they were first flying, trying to achieve the speed of sound. They lost 2 or 3 aeroplanes because they just didn't understand what was going on. So one of the problems that we get is this reversal due to distortion at the wingtip structure twisting. Aileron load, large camber at the rear of the wing section causes the lift force to move rearwards, tending to twist the nose down. And if we're not stiff enough in torsion, if we can't resist the torsion loads, that decrease in angle of attack causes a loss of lift. And same as if we move the aileron up. So the way we get round it is by aileron lockout. Yeah, and what we do towards the wing tip, where the wing section is a lot thinner and more likely to torsional loads, above a certain speed, we lock the ailerons in neutral. Yeah, so once the aircraft takes up, the method of doing it is pretty much aircraft dependent. There are different ways of doing it that we'll have a look at, but the outboard ailerons are locked in the neutral position, and that is known as aileron lockout. Yeah, roll control of the aircraft maintained by using inboard and outboard ailerons and spoilers. At high speeds, we've got to lock the outboard ailerons, known as aileron lockout. So consequently, the inboard ailerons are known as all-speed ailerons, the outboards as low-speed ailerons. And if you could highlight that on page 116, please. Yeah. And the reason for it, if you know the reason, it's the fact that the wingtip isn't stiff enough in torsion, so the wingtip will actually twist, and that will give the opposite effect to the one that we are expecting. Yeah, so your inboard ailerons, low speed ailerons, outboard, inboards all speed, outboards low speed. Yeah, there are different methods of locking the ailerons. One of the ways to do it is through the flaps. Yeah, so when the flaps come to their up and locked position, the ailerons will lock. So depending on the type of aircraft, depending on the type of system that we're going to use, we're going to have a lockout mechanism in each wing to isolate the outboard ailerons from the rest of the system during high-speed flight. It does give an example method. I'll show you that in a second. The mechanism, depending on its position, will either transmit or prevent the transmission of motion from the cockpit control wheel to the outboard PCUs. Lockout mechanism controlled by an electric actuator installed in the housing of the mechanism. And the actuator may be repositioned by a limit switch on the flaps. Flaps leave the fully up position. The electric actuator retracts, repositions the lockout mechanism to separate the pivots. And with the pivot points separated, the mechanism transmits inputs to the outboard PCUs, but when the control wheel is operated. It's a bit of a chew to try and go through it off the sketch, but basically, yeah, what we've got is this little lockout actuator, and the inputs to the outboard actuators above a certain speed. Yeah, let's say the flaps are raised, and what happens? The lockout actuator kicks over, and it locks the input to the outboard actuators. So the quadrant will turn. The quadrant will quite happily mess about. It will quite happily operate. However, the actuator has disconnected that quadrant from the input to the outboard actuators. Once the flaps are selected away from the up position, yeah, the lockout mechanism will retract, and it will allow the outboard ailerons to operate. Does that make sense to everybody? Lockout mechanism controlled by the electric actuator, yada yada. Yeah, actuator may be repositioned by a limit switch on the flap system. Yeah, flaps leave the full up position. The actuator retracts, repositions the lockout mechanism to separate the pivot points, and the pivot points separate. The mechanism transmits inboard inputs to the outboard PCUs when we move the handle. So all that's happening, as I say, it's a pretty pish drawing, but you under normal circumstances, yeah, and the flaps are down, the quadrant will operate, and this pivot here will quite happily put inputs into the outboard PCUs. Once the flaps are up and fully retracted, the actuator extends, yeah, and it stops the input to the outboard actuators, yeah, via this lockout job. Like I say, it's so I'm just going to have a window cleaner coming up a ladder at my window in a minute. I'm going to frighten the life out of him. And then I'll have to nip off for 2 seconds to pay him. So just bear with me if I vanish for a minute. You know why. Where was I going? Yeah. Rather than using the flaps, sometimes again it's kind of aircraft type dependent. I'm not bad, you. If you just ring on the doorbell when you're done, I'll square up with you. Yeah, rather than using the flaps, we can use an airspeed switch. So depending on the speed of the aircraft, we can set the speed up at whatever it might be, and the airspeed switch will have the same effect. Yeah, it'll just send a signal to the actuator. Lockout actuator input to the lockout mechanism. It says it's a 28 volt DC reversible motor. Yeah, don't need worry about that. And as I say, we can use an airspeed switch, or we can use the flap position. But it depends on the aircraft we're looking at. Right, the line there on page 119 about the speed, I'm not sure whether there's a question on that or not. It seems to ring a bell, but I might be thinking of something different. So just to be on the safe side, can you just stick your highlighter through that? I genuinely can't remember whether it came up or not as a question. Yeah, but 220 knots, it sounds about right. Sounds good for having your flaps up and locked. And anything above that, those ailerons are going to get locked in a neutral position. I apologise, I just genuinely can't remember whether it can come up or not. Again, don't worry about the lock-in sequence. Just know that the actuator will separate the outboard ailerons from the system for high speeds, and it will allow operation of the outboard ailerons at low speeds. If you want to waste your time going through it, feel free, but personally, I wouldn't bother. Anybody got any questions? Yeah.
Well, what line we have to highlight? Just please, can you tell us again? Which one?
Yeah, just to be on the safe side, page 119.
119, okay.
Yeah, it's just that bit about the speed, and I genuinely can't remember whether it comes up as a question or not.
Actuator retracts to allow outboard aileron to operate at 220 K.
Yeah, knots.
Knots, okay. Actuator extends above 20 log. Okay, thank you, Jim.
Okay.
Okay.
Anybody got any questions on aileron lockout before we move on? Okie dokie. Spoilers then. Yeah, we know the spoilers. We've chatted through those. Spoilers, often referred to as speed brakes. Flat panels located on the upper surface of each wing. When they're deployed, they'll rise up, they'll reduce the lift and increase drag over the wings, and that'll slow the aircraft down. Yeah, there are two groups of spoilers. Flight spoilers, as the name suggests, get used in flight. The ground spoilers, again, as the name suggests, only get used on the ground. The flight spoilers will operate on both, but the ground spoilers limited to ground use only. Control of them, either manual, hydraulic, or electric hydraulic. Spoilers used to assist the ailerons, providing roll control through differential deployment. Yeah, so if I move the control wheel to the left or the right, we'll get differential movement, and they will help the ailerons during large demands. Yeah, spoilers assist the upgoing aileron. Again, it sounds fairly simple, but page 122, just make a note through there. Spoiler panels are raised to assist the upgoing aileron. Control wheel in the spoiler range, the spoiler panels on the appropriate wing will start to rise up. Further the wheel's turned, the greater the deployment of the spoiler. Movement of the control wheel positions transducers in the form of transducer, rotary transducers, sorry. Yeah, those rotary transducers produce a command voltage signal proportional to the wheel position, and those signals go into what they call the spoiler control module to send out a signal to the spoiler actuator. Page 122 down at the bottom, yeah, note that spoiler operation doesn't commence until the control wheel reaches a predetermined angle. That allows for lateral trimming. Yeah. up at high speed, aileron control is sufficient. So your spoilers for your low speeds. Yeah,
Note
aileron
that
control.
the spoiler does not commence until the control wheel is between this yellow lateral trimming. Aileron control alone is sufficient for rolling control at high speed. The spoiler control can be output and then
Do you want to turn your mic off?
the servo valves sense.
You can
Oh,
take
sorry.
rest, Jim.
Yeah. Spoiler control computer output signals are supplied to a servo which forms part of the actuator. Servo sends fluid to the appropriate side of the actuator and then raises or lowers the spoilers appropriately. And let's have a look at that then. Yep, so our two groups of spoilers, the flight spoilers operate on the ground and in the air, the ground spoilers on the ground only. Yeah, flat panels located on the upper surface of the wing to assist the ailerons in rolling the aircraft, and they assist the upgoing aileron. You can get multiple spoilers. Yeah, again depends on the size of the aeroplane. Your roll control, yeah, your upgoing aileron, the spoilers will rise to assist it. And certainly at low speeds, it's quite pronounced. Quite nice picture, that one. Ta-da! Yep. The spoilers rise proportionately to the amount of hand wheel movement that we're getting. Yeah. The first bit of hand wheel movement, there is no movement of the spoilers, and as we say, that allows for trimming of the ailerons. Yeah. Once we go past that certain point, it says 15 degrees here. I wouldn't worry about that. But once we go past that point, now the spoilers are going to come into play to assist the ailerons with our roll control. Should we want to roll the aeroplane while the spoilers are selected in the speed braking mode, yeah, then roll control will take primacy. So your speed brakes are selected. Yeah, the aircraft's slowing down. We need to maneuver. What will happen is the spoilers on the downgoing wing will remain extended. The spoilers on the upgoing wing will retract to a certain position to give us enough roll to what the pilot's asking for. So that the upgoing wing spoilers will retract proportionately. Yep, there you go. So your roll input, yeah, spoilers will raise the amount it raises, and then the upgoing wing. If we haven't got speed brakes selected, the spoilers will remain in. Again, that's just going over what we've just discussed. Turn the aileron. I think that should read aileron. The control wheel to the left. Spoilers rise on the left wing, the downgoing wing. Speed brake lever deployed. Yeah, left wing spoiler rises. Right wing spoilers move up partially, and the aircraft speed reduces while we continue to roll the aeroplane, bank the aeroplane. Yeah, so they'll work symmetrically or asymmetrically. Asymmetrically, right word? Yeah. Well, yeah, they'll either come out all together or they will come out separately, depending on the control input that we're asking for. Our roll control spoilers. Yeah. So that roll control from the hand wheel, yeah, and what's happening? There's a transducer at the bottom of the control. And that transducer will send a signal off to the spoiler control unit. Spoiler control unit is sometimes referred to as the spoiler computer. Yeah. and that will then send off the appropriate signal to the actuators to tell them where to go to. Actuator piston rod moves within the spoiler actuator. There's a position transducer in there. So as the spoiler controller package is sending out I want you to move to this position, the spoiler actuator is sending back a signal saying I'm here, I'm here, I'm here. Well, yeah, I am where you've told me to be. Once the feedback signal and the command signal match each other, then the spoiler has reached the desired position, and the spoilers won't move until there's another selection. Yeah. If I wanted to, I can change the input voltage by moving the hand wheel. Yeah, and the voltages become unequal, so that the spoiler's going to move again until again the spoilers come back to where that neutral position. Yeah, so you've got yeah, you got your control unit. Control unit is then sending a signal to the actuator. Yeah, and on the actuator there's a transducer as well. So as the jack's moving, yeah, this will send out a signal, move to 15 degrees. Yeah, the signal causes the actuator to move, and as the actuator is moving, this other transducer is sending back a signal. So once the two balance each other out, once those two signals balance each other out, the control unit will stop sending anything out. We're at the selected position. Everybody okay with that? Right. Speed brake control. Yeah, if I want to operate the speed brakes, there's a speed brake lever on the throttle quadrant adjacent to the throttles. Yeah, the speed brake lever will operate the speed brakes in the air or on the ground, and again it operates a transducer which is providing the command signal to the control pack of the spoiler computer, and that control pack will tell the spoilers whereabouts they need to be. Yeah. Operates the spoiler actuator, and the spoiler panels are deployed to the maximum angle, airborne mode or ground mode. Yeah. Placing the speed brake lever in the flight position raises the flight spoilers to predetermined positions. Yeah. Solenoid operated device stops the speed brake control lever at the flight position when the aircraft is in the air. So what we've got on the side of the throttle quadrant, we've got the speed brake lever. Speed brake lever has fully down position, so the spoilers are all down. Has an armed position. There's a flight detent position and then an up position. Excuse me for 2 minutes. I've just got to go and give this chap his money. I won't be a sec. My apologies. Well, people need paying. Where do we get to? Yeah. Down, armed, flight detent position, and a fully up position. At the bottom of the lever, yeah, there is a transducer looking for the position of the speed brake handle. Also incorporated is a little actuator, the auto speed brake actuator. When we go, we're going to go to land. Yeah, the pilot's going to put the actuator, the lever in the armed position. Once we're in the armed position, so long as we meet certain criteria, that auto actuator will extend and it will drive the spoilers, flight and ground, to the fully up position. Yeah, so speed brake lever provide for operating the spoilers as speed brakes, either in the air or on the ground. Lever operates a transducer, produces the command signal for the control computer. Output signal operates the spoiler actuator on the spoiler panels, and the spoiler panels will deploy to the selected angle, airborne or on the ground. Putting the speed brake lever in the flight position raises the flight spoilers to predetermined positions. Yeah, so they won't go straight to their fully out position. Depending on the speed of the aircraft, they'll slow down to through various levels. Solenoid operated device stops the speed brake lever in the flight position while the aircraft's in the air, so we can't go to the fully up while we're in the air. Before landing, yeah, pilot lifts the speed brake lever from the down position detent, places it in the armed detent for auto speed brake operation. On touchdown, that little electrical actuator moves the speed brake lever to the fully up position, and the flight and the ground spoilers will go to their fully out position. But before it'll do that, and what page are we on? We are on page 127. Yeah, the first lot of bullet points. So before the spoilers will deploy automatically, both landing gear have got to be on the ground. Yeah, it says the bogey's not tilted. So basically the weight of the aircraft has got to be on the ground through the WOW switches. The thrust levers, throttle levers have got to be at idle. The wheels have got to be rotating above a certain speed, and the speed quoted here is 60 knots. And there's got to be no faults in the system. Yeah. The pilot can override the auto selection system and select the speed brakes down. The speed brakes will automatically retract if a go-around's initiated, or if electrical power is lost for any reason. Yeah, they'll automatically extend if we've got a rejected takeoff, when the throttles are retarded, brought back to idle. The wheel speeds exceed 60 knots and thrust reverse is selected. While we're talking about spoilers, if we say where it says if electrical power is lost for any reason, they will automatically retract. They do, and they come in very, very quickly. So if you are working on a spoiler system at all, yeah, make sure that the ground locks are fitted for the actuators. Yeah, if you've got your fingers in there when the spoilers retract, you'll never pick your nose again. Yeah, they'll sever your fingers without a problem. So watch for that one. Yeah, so in the speed brake life, yeah, we've got the down, we've got the flight detent, we've got fully up and the armed position. The auto actuator, if we go to the armed position, we meet the criteria that we've just said. Yeah, then on landing, as soon as the wows have made the aircraft waits on the ground, wheels are rotating. Yeah, then the auto actuator will drive the speed brakes from the armed position to the fully up position. That is both ground and flight spoilers will whack out. Yeah, both spoiler and the speed brake systems are operating. The input from one system will modify the position of the surfaces as determined by the other. So if the speed brakes are raised and then we roll the aircraft, the spoiler panels on the upgoing wing are lower. The other thing, and again, it's worth noting on page 127, spoiler position is modified by the aerodynamic loads on the spoiler surfaces. So when the air loads cause the hydraulic pressure in the actuators to reach a certain value, the hydraulic pressure is relieved, and that prevents the spoiler from moving further up. Yeah, so that's what they call spoiler blowback. It's there as it protects the structure. So if we're going too fast and we put the spoilers up, yeah, the air loads will push the spoilers back down, not all the way, but to a predetermined level. And then as the aircraft slows down, that allows the spoilers to come back out. Yeah. Right, spoiler and speed brake systems electronically controlled by a fly-by-wire system. We've got no manual reversion. So system described the spoiler power control actuators are signaled electrically. What we got? We've got the spoiler PCU. That's your spoiler control panel. When it talks about EHV on the slide, that's electro-hydraulic valve. That is our servo, essentially. Yeah, so you're going to get hydraulic power into the actuator. Your servo's there, and in the actuator we've got this transducer that's feeding out the position of the actuator. Spoiler control unit, or computer, if you prefer, is monitoring various parameters. It's looking at the amount of input from the hand wheel, the roll input, if you like. It's looking to see what the speed brake selection is. Yeah, it's looking at throttle position. It's looking at the wows. Yeah, and it's looking at the position of the auto actuator. Have we gone to that armed position? And from there, provided the conditions are right, or if we wanted to move the ailerons, for example, yeah, it's going to send that signal to the servo. Actuator will move. The transducer in the actuator is sending the signal back, and that's going to back off the input coming from the control unit. Yeah. Do I need to say anything else, really? That's just another what we're saying. Your rotary transducer at the bottom of the stick, sending in the required demand to the spoiler. I'll call it the computer just for ease. Yeah, so the spoiler computer looking at that. It's looking at the auto actuator. Yeah, what the required position is on the auto actuator. So it's looking at that. Sorry, yeah, and then depending on what we want, it's going to send out a signal to the spoiler actuator. Spoiler actuator, it's going to move the spoilers, and as the spoilers are moving, as the spoiler actuator is moving, that transducer there is sending a signal back to the computer. So, right, I'm moving, I've stopped. I'll come back to that in a second. Just go through this bit on page 128 to make sure I haven't missed anything. We've talked about the signals being mixed in the computer, proper amount of output for the required demand. Moving of the control wheel or the speed brake lever operates the transducer. Yeah, and it's looking at the wow switches. It's looking at the truck tilt if we've got bogie undercarriage, to make sure that the full weight of the aircraft's on the ground. Thrust lever position. If we're on the ground and we advance the throttles, then the spoilers will all retract. Deploy the spoilers on landing if the throttles are retarded. And then it'll look at the speed brake lever position to make sure that we've got that symmetrical operation. Airspeed, yeah. The spoilers might not necessarily, if we've got a group of, 6 on each side, it may be we're not going to operate all of the spoilers together. It may be that they're going to go to different positions, or some of them are going to be locked out. It depends on the aircraft type, depends on the information from the air data computer. So some aircraft, you're not going to get them all deploying at once. It's just easy to describe it all like that. Flat position, it may be used to limit the roll spoiler deflection with different degrees of flap. System faults which affect operation of the spoilers, indicated by amber lights on a warning panel. If that happens, yeah, the pilot's got a ability to, operate the speed brakes manually. So it says there, that's that little lot, that's that little lot. That's that little lot. Right. System indications, yeah. If we get a failure in the spoiler system, we'll get an amber caption or an auto speed brake caption, and the pilot can operate the speed brake lever manually. So if we get a failure in that little auto actuator, yeah, rather than allowing the actuator to do the work, the pilot can make the selection. Yeah. Everybody okay with that? Any questions there?
Jim,
Yeah.
so what about this input aileron control wheel RBDT for the control unit? For what purpose?
That is the rotary position transducer, and that is telling you what roll inputs he wants. So that rotary transducer is feeding in the signal, the required amount of roll spoiler that's wanted.
This means which one whether we want to deploy the spoiler partially or
is that the picture you're looking at? The aileron control wheel RVDT?
Yeah.
Right.
Does it decide the amount of deployment that we are going to deploy the spoiler partially or fully? Does it
so the picture on 130 is this one. Yeah. And what he's doing when he turns the hand wheel, he's operating this transducer. An old RDVT or RVDT, it's rotary variable differential transducer. So basically, as he moves the hand wheel, that transducer is sending a signal into the spoiler computer. So that rotary input is saying to the computer, right, we need to move the spoilers 20 degrees. Yeah, so the computer will know that 20 degrees of spoiler is 20 volts, for example. Don't worry about the figures, I'm just making them up. But it'll say, right, we want 20 volts of movement. So it'll send out a signal to the actuator, to the servo. Yeah, it'll say 20 degrees of movement, and the actuator will start to move. As the spoiler starts to rise, there's another transducer, and that's saying, right, 15, 20 volts of movement. Yeah, so it's constantly feeding back voltage from the actuator. And as soon as the voltage from the actuator and the voltage from the selector, if you like, the hand wheel, as soon as they marry up, that's the thing neutralized. So the spoiler will stay in that selected position. If he decides to put a bit more roll in, yeah, then the voltage here is going to go up. So the voltage coming out will go up. The spoilers will move. But as the spoilers are moving, yeah, that transducer is again sending back a signal. So the voltage here, the voltage from here, again, eventually meet the point where the match, and that neutralizes the signal again.
Okay, Jim.
Does that answer your question?
Yes.
Okay.
Thank you.
Okay, and then the other bit, the air grounds, your wow switches, your throttle levers, speed brake lever, flat position, speed sensing are all that information is being fed into the computer to make sure that we'll get the right deployments at the right point. Spoiler actuator. Spoiler actuator is taking in signals, as we say, from the spoiler computer. Yeah, the actuator is held in the retracted position by little locking fingers. Yeah, the little locking fingers are there to make sure that the actuator isn't sucked up by the low pressure that's flowing across the top of the wing. Yeah, so the actuator is mechanically locked by a spring acting on the lock piston. I'll go through the operation in just a second. But the idea is the spoilers are sitting flush with the top of the wing. And if you think back to our aerodynamics, as the airflow goes across the wing, it's creating a low pressure. And if we didn't lock the spoilers down, that low pressure could start to pull them up, so that they'd start extending into the airflow, and that would make life uncomfortable. So what they do is they have these what they call locking fingers, and the locking fingers just engage behind locking lips. So it's just a little face on the inside of the actuator. Yeah, if I want to extend the actuator, yeah, I'll put a dose of hydraulic pressure in. Yeah, hydraulic pressure at the back on the piston. Yeah, causes this internal piston to retract against spring pressure. As that retracts, it allows the locking lips to come inwards. Yeah, so you've got hydraulic pressure. That's my nickel pen. Go red because I like red. So we've got hydraulic pressure coming in, and it's all acting in here. It's also going to act on this plate here, and as it acts on the plate, it's going to push this piston back against the spring. As it pushes the piston back, it allows these lips to, or allows the fingers to squeeze inwards. The hydraulic pressure acting on these faces are going to push the fingers down. So now that hydraulic pressure that's in here will extend the actuator. Yeah, and the whole purpose of those wee things is to keep the actuator locked when we're selected down. If I want to select the spoilers down, yeah, hydraulic pressure into here. That piston will push back, pulling the ram in, and at the same time as the ram retracts, yeah, the little valve at the end here, spring pressure is pushing it out, and as it pushes out, it's pushing the fingers back behind the lips, and so locking it in position. Yeah, and that's what that little lot's about. So remember, again, under that top paragraph on page 131, yeah, if the actuators were not locked, the reduction in pressure over the top of the wing would raise the spoiler into the airflow. Actuator controls spoiler position through its full range of travel. Yeah, speed brakes, they're either down and locked, they're armed, they're in the flight detent, or they're fully up. Speed brakes may be manually positioned by means of the speed brake lever in any desired intermediate position. So between the down position and the flight detent, yeah, the pilot's got the option of selecting anywhere within that range, and if he goes into the flight detent, then they will go to the predetermined position. Coming into land, what it'll do, it'll turn out of the flight detent to the armed position. Once we're in the armed position, so long as we meet all those criteria, once the weight of the aircraft's on the ground, the wheels are turning, throttles are at idle, then that actuator will drive the spoilers up to their fully up position. And again, when we're in the right position, that's it. Maintenance of the spoilers. Yeah, as I say, if you are doing any work in the spoiler area, you must have the ground locks fitted, the safety locks, with the appropriate streamers on so you don't get left in position. Make sure that the hydraulic system is depressurized and any electrical connectors or CBs tripped and clipped before you put your fingers in there. If you're putting spoiler locks in, yeah, or tripping CBs or disconnecting plugs, make sure you cover it in your paperwork. Yeah, again, just to cover your own ass, but yeah, do make sure you fit the correct equipment. Aircraft we were working on, the guy was working on the spoilers on top of the wing, and he had the spoiler up, but we didn't have a gag. Yeah, we didn't have an actuator. And the actuator fitted about there. That was the ram. That was the actuator. The actuator's pivot at this end, so you can account for that angular movement. But the guy that was working on them didn't have a ground lock to put in. So what he did, he put a chock, quite sensibly to save his own fingers. He put a chock under the speed brake. Yeah, and he was working away quite happily. And one of the B2 guys that we had knocked the ground power cable, so we lost electrics, and of course the spoiler immediately started to come in, but because the chock was there, it couldn't retract far enough. But 3,000 psi pulling on the spoiler, pulling on the chock, did an awful lot of damage to the wing structure in that area. It was a real mess that it made. The guy didn't lose any fingers, but we certainly spent a lot of time repairing the aircraft. Yeah, so use the right stuff. And as I say, if you're putting them in, tripping and clipping or anything like that, make sure that you raise the right paperwork. Was it can't remember what module it is. One of the incidents that is human factors. One of the famous human factor incidents was where the guys had been working on the spoiler system on was it 737? Can't remember. But there's a maintenance position for the spoiler selector, and again the guys had selected the maintenance position, hadn't reset, and the aircraft tried to take off. The spoilers started to rise, pulled up by the airflow. Luckily enough, they managed to control the aircraft and get it back down on the ground, but could have had nasty consequences. So again, working on these things, follow the manual. Yeah, follow the maintenance manual. Let's say a little pivot on the bottom of the jack, just so as it extends, the jack body can move, so you don't get any undue stress building up. Down date end, yeah, we know about that. All retracted, armed for the automatic side of things. Once we touch down, speed brake handle, the little auto actuator will drive it to the upper position, the flight and the ground spoilers. Flight day end, spoilers extended to the maximum position for in-flight use, and positions in between. The pilot can select positions between the two for different deployments of spoiler that he wants. That's your speed brake lever. Yeah, you're down, you're armed, the flight date end, and the fully up. This is quite handy because remember we talked about the green range when we're talking about the variable incidence tailplane, and that's an example of the trim wheels here, the amount of trim indications here, and we've got to make sure that our pointer is in the correct range for takeoff. Let's just see what else we need. We've done that, we've done that, we've done that. What we'll do, we're doing quite well, so we'll just have a wee break there. 14:45 to me. Let's say 15 minutes. Yeah, I make that 14:45, so 1500 my time. 15 minutes in Kathmandu will be 20:30. 20:45 for you guys. Yeah?
Okay, Jim.
Is that 20:30 with you now?
Yes, Jim.
Yeah, okay. So 20:45, 15 minutes. And then we'll wrap this little lot off. Okay?
Okay.
Okay. All right, just give it 1 more minute and then we'll plod on. There's not a hideous amount left to finish off now for where we need to be today. We've done rather well. So if anybody's got any questions on anything towards the end of the lesson, please just let me know. Yeah, but I am following it in the notes as we go, and everything that I've sort of recognised so far, I've let you know. So we haven't missed anything, and hopefully highlighters are working quite nicely. All right, so before we plod on, anybody got any questions? Nope. All right. Where we're going next then? Yeah. Yeah, just idea of your control layouts, just typical indications you might get, your ICAS indications, your CWP indications, your spoilers aren't working, or your auto brake's not working, speed brake lever that we talked about with the different positions. Yeah, oh. And then the good old yeah, spoiler actuator type thing. Do we really need to go into that? We looked at the plain and simple and straightforward mechanical hydraulical selector actuator. This is just the electro hydraulic actuator. Just to give you an idea, we don't need to know the internal workings, but just to give you an idea, what we've got is our servo valve. Yeah, the servo valve is biased to one side using a spring. Yeah, very similar to our transfer valve. What we've got is a swiveling pipe. And that swiveling pipe is responding to signals from the spoiler computer. Spoiler computer will send a signal, and it'll cause that swiveling pipe to move. Yeah, swiveling pipe has pressure from the main hydraulic system being fed to it, and as we get a signal, that pipe is going to move. As it moves, it's going to transmit pressure to one end of the servo or the other. Yeah. So in this case, it's pushing pressure down the servo. Yeah. Assisted by spring pressure. The servo is being biased towards the retract side of things. The other side open up to return. And there's an LVDT, a linear transducer, telling the spoiler computer what position the actuator is in. Yeah, so in this case, it's fully retracted. Yeah, we want to keep it on the retracted side. We want to hold it on the retracted side. So main system pressure and that spring is keeping the actuator in the in the retracted position. If I want to extend, make an extend selection to wherever it wants to be, and the computer somewhere in there will move the swiveling pipe. That swiveling pipe, depending on the degree of movement it's going to get, is going to send hydraulic pressure to the other end of the servo. The other end of the servo is now going to push against the spring. Yeah, as it pushes against the spring, it's opening up this half of the actuator to pressure. Actuator is now going to extend the selected amount. The transducer's talking back. Yeah, and once we reach that point, once we reach that point, the signal will cut off. Yeah, so the spoiler will be held there till the next input from the control requirements. That little feedback spring is just there for accuracy, the accuracy of the movement that we want. And again, yeah, as I was saying, if you lose electrical power, this thing is biased towards the retract end. So hydraulic pressure, you've got no electrical signal pushing the servo in the opposite direction. So now with spring power and hydraulic power, the servo is just going to slam across and cause that actuator to retract very, very quickly. So whatever you do, mind your fingers. Tail unit speed brakes, yeah, we looked at those the other day. Large transport aircraft fitted with spoilers on the top surface of the wing, and the speed brakes or the air brakes form part of the tail cone. Just two petal panels hinged at the forward edges and extend either side of the fuselage centerline when they're selected out. When they're closed, they form the tail cone of the aircraft. Tail-mounted air brakes, extended and retracted by hydraulic actuators. Selector valve in the cabin. Selector levers operated in a quadrant which allows the air brakes to be selected over 4/5 of the movement range. Lift dump spoilers remain retracted. Then when we've landed, we move the selector, and that operates the lift dump spoilers, and it also pops the air brakes out to their full extent. So the lift dump spoilers lift over the wing, they increase the drag, and the tail cone increases the drag as well. Yeah, that's the things there, form part of the tail cone. Yeah, select air brakes, they will extend, as I say, to 4/5 of their full travel. Once the aircraft's down on the ground, the pilot can select the lift spoilers out, or the lift dump effectively. Yeah, aircraft's on the ground, the spoilers will deploy over the top of the wing, the airflow will be destroyed, and these will pop out an extra, whatever it is, 1/5 of the whole range of movement, and then popping out is going to create all that extra drag. Yeah, what? Yeah, don't think there's anything on that page. If there was, it'd just be the fact that in flight you get 4/5 of the lever range, and then on the ground you've got that extra bit of movement. The slides on the screen just showing the air brakes that are forming the tail cone of the aeroplane. And then there's a couple of examples just of other types of air brake that are fitted, albeit military aircraft, but they're all fulfilling the same function. They are there to slow the aircraft down in the air. If you think about it, throwing a great big slab of metal out into the airflow is going to have the desired effect. Yeah, so yeah, your lift dumpers. Yeah, in this case we've got roll spoilers. Yeah, and then purely your lift dumpers, your ground spoilers. At the back of the aircraft we've got the air brakes, and the air brakes tail cone when they're closed, and give plenty of drag when they're open. The selector lever. Yeah, they're either in. Yeah, I can select them out, and then that lift spoiler, as we go down to the lift spoiler, we get an extra movement of the air brakes. Again, on the throttle quadrant adjacent to the throttles, and you got your trim wheel there for your pitch. And again, just showing the difference in spoiler position for different speeds. Yeah, some will deploy a bit further than others until we get to the required flight detent position, where they will all deploy to their maximum point. Your speed brake lever we've already mentioned. Yeah, the different positions, and again your trim wheel. And the trim wheel with a little handle that pops out. You can wind the wheel to move the variable incidence stabilizer, and again it's a bit better. You can see the pointer. You can see the green range on the trim indicator, and so long as we're in the green band, we're in the safe range for takeoff. Hey, anybody got any questions on any of that so far? Wonderful. Right, the last main control surface that we need to look at is the rudder. Yeah, the rudder giving us yaw control or directional control about the normal axis or the yaw axis. Yeah, and it is just a large control surface placed on the back of the vertical stabilizer or the fin. Yeah. System similar to the manually operated system, except that the pilot's inputs go to PCUs, which operate the rudder. Trim, feel, travel limiting, all incorporated in the system. Yeah. The system described in the notes, inputs at the pilot, the co-pilot's pedals, transmitted by a single cable loop to a quadrant in the rear fuselage. From the quadrant, the motion's transmitted by a push rod up to the rudder bell crank, and from there to it says the rudder servo, and the rudder servo is the actuator. Yeah, you've got a field trim spring cartridge or a bungee in the system to give us that artificial feel. System described, we've got I think it's 3 hydraulic systems, 2 tandem actuators. Inputs from the AFCS, the flight control system, avionic flight control system, to give us our autopilot inputs. There is a yaw damp input into the rudder. We'll go through that. That's going to null down our Dutch roll. Yeah, rudder trim inputs at the trim wheel, transmitted by a cable loop to the trim actuator. Movement of the trim actuator changes the neutral position of the spring and transmits movement to the servo on the actuator. Ta-da! Right, so rudder, yeah, large control surface stuck at the back of the fin. Depending on the size of the aircraft, they are often duplicated, so you have an upper and a lower rudder, and again that duplication allows for redundancy as well. So even though the thing is split, if you get a failure in one system that's driving one section of rudder, the airflow coming down either side of the fin, because the fin tends to be a symmetrical aerofoil, yeah, the airflow is going to keep the non-moving bit in the neutral position. Yeah. Yeah, small aircraft, mechanically driven from the rudder pedal. Well, they're all driven from the rudder pedals. Yeah, just this one uses mechanical inputs. This one uses hydraulic inputs. Yeah, your rudder pedals, one for the pilot, one for the co-pilots. Yeah, off to via a torque tube to your quadrant. Converts to linear movement. Yeah, your control cables. And then again, via a quadrant at the back, that input is again converted via the bell crank to push-pull rods. and the push-pull rod's connected to the servo on the main rudder actuator. Yeah, your actuators, again, depending on your multiple systems, multiple actuators. The feedback, yeah, we want to know what position the rudder's in as we move it. So we've got the feedback going in there, and somewhere in there we're going to have our feel, and we've got our autopilot inputs into the control cable system as well. This one, I've got to be honest, it talks about the forward rudder and the aft rudder. I've not really come across that as a system personally. Yeah, but it's obviously applies to some aircraft where your rudder is split into two sections, the fore and the aft section. So as you move in the forward section, the PFCU's attached to it, then via these little control links, the aft rudder is moving appropriately. I'm kind of guessing that movement of the forward rudder, the way the linkage is set up, it's just going to make sure that you get the right amount of movement on the aft rudder, and that could be used as a sort of movement limiting method as well. Rudder limiting, yeah, to decrease the available rudder travel with increasing airspeed. So the faster we go, the more we're going to reduce the amount of travel available to the rudder. Different ways of doing it. We can do it by reducing hydraulic pressure being supplied to the actuators. So as speed increases, pressure is bled off. We can use a ratio changer, which changes the rudder travel in relation to the rudder pedal travel. So the faster we're going, yeah, the ratio changer, the more we press the pedals, the less movement we're going to get at the back end. And as we'll see in a minute, we can use a Q-pot as well for the rudder. By using a Q-pot, yeah, we're using pitot-static pressure, and faster we're going, yeah, the more the pitot pressure is going to increase. So we can use that to form a limiting system. Right, what else do we need to say there? No, just a schematic. Your pedals, the interconnect between the pedals, your cables to your quadrant. We've got a trim set up on the rudder as well. Yeah, we can alter the rudder trim just to correct for that flying fault. The rudder feel tends to be just a spring. Yeah, so the harder you press the pedals, the more you're compressing a spring, the more resistance you get. So that's giving you your feel, and that's quite handy as well for limiting the rudder movement at higher speeds. Yeah, so fighting against a spring and against the air loads that are striking the rudder is going to physically limit how much the pilot can move. Yeah, rudder servo. Yeah, and the rudder servos sending out movement to the actuators. Yeah, dual actuators moving the rudder left or right. Yeah, the feedback rods are just again nulling. Remember we talked about the ram mounted and the body mounted actuators. In this case, it's a body mounted actuator. It's the ram that's doing the moving. So we put that linkage in to make sure that the servos go to the null position when we get to the required point. Yeah, and then autopilot inputs there as well. Yeah, your rudder limiters, the setup we've got, as I said, what we can do is the faster we're going, we can bleed off the pressure to the rudder actuators. So eventually, we've got that little pressure. We can't really move the rudder. The rudder itself, as I said before, is held in a neutral position by the airflow because it's a symmetrical aerofoil. The ratio changer, is just limiting the faster we go. It's just limiting the amount of movement we need on the rudder in comparison to the movement on the pedals. The Q-pot is a great little thing. It's just a little telescopic device. It's got pitot pressure going into it. It'll have a bit of static going in as well, just to compensate for altitude. But the faster we go, the more the stepped stop, as they call it, it's just a bit like a car aerial. It collapses in on itself. So the faster we go, the more the dynamic pressure pushes out the Q. Should I call it the I'll call it the cone because I can't think of the right word. So the dynamic pressure is going to push the cone out. This claw stop is, as the name suggests, and as you move the rudder pedals, the claw just moves left or right slightly. As we get to higher and higher speeds, because this cone is growing, it's going to limit the movement that the claw has. And obviously, the more that claw movement's limited via the control linkages, the less movement you're going to get on your rudder pedals and at the rudder. Yeah. So eventually, this will go all the way out, and it'll just about stop any movement of the rudder as the aircraft slows down. Yeah, as the dynamic pressure reduces, then the claw will start to retract, or the cone will start to retract and enlarge the range of movement on the claw stop. So faster we go, the more the stop reduces our movement, reduces the movement we've got available to us. The slower we go, the more movement we get. Yeah. So it calls it a stepped cone in the notes there. Yeah. Attached to the Q-pot, supplied with a peak and static pressure. Step cone restricts the movement of the claw-shaped stop, which forms part of the rudder operating system. Increasing speed, step stop. That's very difficult to say at high speed. Step stop. Step stop is moved into the claw, restricts the rudder movement, speed reduces. Yeah, the cone retracts. Yeah, and allows larger amounts of rudder travel. It says the rudder trim system is coupled to the Q-pot limiter so that equal rudder travel is always available at the trimmed position. So the Q-pot stop is always repositioned to be central over the stops. Rudder system may have a duplicated control run to provide severance protection. So when Yadav goes mad with his scissors, yeah, we've protected against that. Forward rudder operated by the control system. Aft rudder is linked to the forward one and moves as a function of forward rudder deflection left or right. And that system has manual reversion as well, should we need it. Ta-da! Yeah, we said before, just go back a step. It's worth just thinking about it, making a note of the ways that we can limit rudder travel. Yeah, certainly the Q-pot limiter, a ratio changer, or reducing the hydraulic pressure, because it could be a question comes along, what methods could we use to limit rudder travel? Could we use internal locks in the actuator? Could we use a Q-pot limiter? Or could we increase the hydraulic pressure supplied to the actuators? Yeah, it might be something along those lines. So the methods of limiting that's on page 137, just make a note of that with your little coloured pen. All right. Yeah, yaw damp. We said that all aircraft, especially those with swept wings, subject to yaw damp, subject to Dutch roll. Sorry. The way Dutch roll is damped out varies, but most swept wing aircraft will have a yaw damping mechanism built in. Sudden gust or short uncoordinated rudder movement produces a yawing motion, which in turn starts the Dutch roll kicking off. The fin and the rudder tend to offset the yawing motion, and stability is regained slowly but surely. Some aircraft, Dutch roll may not be much of a problem. Well, all aircraft have got a tendency to Dutch roll, but others may just correct themselves, just the pure design of the aircraft. Some aircraft that natural damping tendency, yeah, is fine, but for other aircraft we need to build in some sort of assistance to the aircraft. Yeah, some aircraft, natural damping of Dutch roll is more effective at high speed than low speed, and in some cases the rudder is going to be used to assist the fin in its stabilizing and damping out of that yaw movement, that Dutch roll. Yeah, so that assistance to help damp out the Dutch roll is referred to as yaw damping. Yaw damping system is designed so it can be operated independently of the AFCS, the Avionic Flying Control System. So even if the aircraft's being flown manually, yeah, Dutch roll can still be counteracted. System can be switched in. Yeah, I'll switch it on by selecting a damper position on the AFCS panel, or by selecting a separate yaw damper switch in the cabin. If we've got separate rudder sections, i.e. an upper and a lower rudder, then each rudder section will have its own yaw damper. Right, just going through, yeah, the yaw damping system. The main component is the coupler. Yeah, the coupler has a gyro in it, and that gyro powered from the aircraft electric supply. Coupler contains processing circuits and provides signal amplification. That amplification, that signal, is supplied to the transfer valve of the rudder PCU. It's the transfer valve that moves the yaw damp actuator, and the movement of the yaw damp actuator moves the main actuator. Yeah, so just going off the thing, that's your rudder, although it doesn't look like a rudder, but that's your rudder. The coupler unit is in there being fed off the 115 volt AC supply from the aircraft. The coupler unit feeding in signals to a yaw damp actuator. The yaw damp actuator is just a little, normally a little electric actuator. Pretty much our transfer valve. Yeah, transfer valve directs fluid into a yaw damp actuator. Movement of the actuator piston transmitted to control valve in the main actuator, which then via its piston rod moves the rudder in the required direction. Yeah. Coupler unit. yaw damp actuator, imagine that as the transfer valve that we looked at earlier. Yeah. What it's saying in the screed, and it's a bit shittily written. The transfer valve, yeah, is going to put signal into transducer, and the transducer is going to cause the main actuator to move. The main actuator moving is going to move the control surface, the rudder itself. Yeah. As the main actuator is moving, yeah, the transducer is giving feedback to the coupler. So the coupler is saying, right, I want 10 degrees of movement. The transducer is saying you've got 10 degrees of movement. The main actuator is just saying, I've moved there 10 degrees. Yeah. That feedback signal may be supplied to a position element indicator. I'll look at that in just a second. See if I've got a better picture. No. Yaw damp switching system switched on. DC power applied. Being energized, a relay completes a circuit to a solenoid in the PFCU, allowing hydraulic fluid to flow at the transfer valve. Yeah, and that extinguishes the fail light. When the system's switched off, it's got a fail light. Once it's switched on, fail light will go out. Yeah, that's if you remember the solenoid that I was talking about this morning in the transfer valve. Yeah, that's totally lost what I was saying now. Yeah, solenoid in the transfer valve turns the system on, allows fluid to flow through to the transfer valve servo, which is ready to operate the main system and put the inputs into the main actuator. Test switch, yeah, we've got a test switch, so we can operate the test switch, and that will flick the rudder left or right accordingly. Bottom of page 139, yeah, the yaw dampers move the rudder approximately 3 degrees either side of neutral. Yeah. So here we go. We're going to go flying. Yeah, we're starting everything up. We turn on the yaw damp system, press a test switch, and that's just going to flick the rudder left or right. Just make sure that the gyros are working and that the actuator is working. Autopilot, yeah, the autopilot, that's feeding in its inputs to the coupler as well, and the coupler again we're talking the yaw damp actuator. In this case, we're talking the transfer valve, exactly as we saw this morning. Yeah, where do we go from there then? Yeah, yaw damp actuator, yeah, operates the rudder. Operates the rudder only if the actuator moves the rudder pedals and the rudder. It's called a parallel actuator. Some aircraft, yeah, the yaw damp system is entirely independent of the rudder controls. Yeah, so the yaw damp can flick the rudder either side of neutral, and the pilot will know nothing about it. Yeah, that is your series actuator. If the actuator, if you get feedback and the rudder pedals move when the yaw damp moves, that's a parallel actuator. The yaw damp control system, yeah, the yaw damp light, yeah, we turn the system on, yeah, and the light goes out. Yeah, if the light's on, the system's not working or it's switched off. Yeah, once it's all up and running, yeah, there's a yaw damp indicator adjacent, and the yaw damp indicator will flick left or right, letting him know that the rudder has moved. Yeah, just indicates yaw damp movement of the rudder. The pilot pedals aren't indicated. Again, if the system requires, then the pilot's going to feel the movement through his feet anyway. Anything else we need to say there? No. Yeah, rudder trim. Rudder trim, yeah. The trim actuator, the motor's powered by 115 volts AC. The trim indicating system, 28 volt DC. Don't worry about that. It's just getting supplied with aircraft electrical power. Rudder trim switches operate. It operates a pair of contacts. Again, we've got the two contacts, yeah, the armed and the control. Trim actuator, yeah. The electromagnetic brake prevents the actuator overrunning. There's internal mechanical stops. We've talked about all of this lot to prevent the thing from running away fully. Trim commands from the trim switch cause the actuator to extend or retract, and that rotates the field and centering mechanism. Yeah, drives the power unit input rods to the position of the rudder's new neutral. Pedals are positioned to a new neutral position corresponding to that of the rudder. Worth noting, if we put rudder trim in, the rudder pedals are going to move as well. The trim indicator, yeah, is a electrically driven indicator from a transmitter in the trim actuator, graduated in units of trim left or right, and the indication is by a pointer on the tape that rolls left or right to indicate. Just, yeah. Our rudder trim controller, yeah, I'll go back to that other picture with the electrics on in a minute. If I want to move the nose left or right, I'll turn the switch. The switch is sprung loaded to center. Yeah, so if I want to go nose left, I'll flick the switch nose left and apply the amount of units of trim to get me to where I need to be. Yeah, and the trim indicator will tell me how many units of trim I've got applied, left or right. Yeah, if the power supply to the indicator is lost, the tape and the pointer roll off to the right. Yeah, and we get an off light appears. So if you get a loss of power, yeah, that tape rolls the pointer off the scale to the right, so the whole thing will just trundle off that way. Yeah, and that is your indication that you've lost power. That's on the bottom of page 143. Yeah, and that is well worth sticking a highlighter through as well. Yeah, if you lose your power supply, the indicator, the tape rolls the pointer off the scale to the right, and we'll get an amber caption on the left as well. Okay. So your trim indicator, you got your trim actuator.
Hello, Jim.
Feeding back.
Hello.
Yeah.
Which paragraph to highlight? I'm not getting it.
The very bottom one, page 143.
The indication. Yes.
The indication,
is by pointer on a black tape that rolls left or right to indicate the units of trim.
Yeah.
The power supply to the indicator is okay. Okay, thank you, Jim.
That's the bit, the power supply. So you're flicking your switch left or right. Yeah, your rudder trim's sending a signal into the actuator. Whichever way you're going, left or right. Yeah, the actuator will move left or right. The transducer there will send a signal to the trim indicator. Trim indicator will then say how many units of trim you've got applied, and if you lose power, it's going to trundle all the way off to the right. Yeah. The aileron, that was the picture that we looked at earlier with the aileron trim switches as well, and we'd either flick them left or flick them right. Two switches for your armed and your control, and they've both got to be pressed at the same time as well. Right, that was our flying controls. Right, safety precautions for powered flying controls. Always follow the procedures in the maintenance manual. Yeah, powered flying control systems can be dangerous. So before moving any controls, make sure that the aircraft around the control surface is clear of both people and equipment. Yeah. When you've finished your work, because it's pressurized systems, just make sure that the accumulators are depressurized. Otherwise, there's still potential for the control surfaces to move. And do not move trim wheels or trim switches when hydraulic power is released, because the hydraulic power is put back on. The control surface will go to the position it was told to. So with your trims, yeah, the electrical signal still going to the actuator. Yeah, as soon as you reapply power, the actuator is going to try to take up the selected position. So always follow the manual procedures. And that, guys, takes us up to exactly where I want to be for today. Yeah, we've covered a fair amount of material. We've done well today. Hopefully we've managed to highlight all the relevant bits to us, and hopefully we've managed to get a bit of an understanding of the subject as well. So we're about 20 minutes ahead of where we should be. What I'll do, I'll dig out the questions for this. As I said before, some of the material we're going to. Hang on, what day are we on? Yeah. Right. It's Monday today, isn't it? Right. There's no point in pushing too hard. What we'll do, we'll finish this off tomorrow. Tomorrow morning, we'll finish flying controls, and then we'll start on landing gear tomorrow afternoon. Yeah. There's not a lot left to wrap up in the morning, so we'll do that. We'll finish there. We'll cover fly-by-wire and the high lift and all the rest of it tomorrow, and then we'll cover landing gear tomorrow afternoon. Has anybody got any problems, any questions, anything there? Is everybody okay with finishing 15 minutes early?
All okay, Jim. You can leave now.
Right. Okay, so if anybody's got any questions, I'll be online for a few minutes. Failing that, give me a shout in the morning and we'll cover any points in the morning. We'll finish flying controls tomorrow morning, and then we'll start landing gear tomorrow afternoon, and we'll finish that off on Wednesday. Again, landing gear, it looks like a big book, but there's not a horrendous amount to it.
So are we getting some more questions for flight controls?
Yes, I'll dig them out now when I've finished, and I'll send them to yourself for onward transmission.
Okay, all right.
Okay.
Okay.
Right. Oh, well, if nobody's got any questions, yeah, we'll do it that way then.
Okay, okay.
Have a pleasant rest of the evening. I know it's nearly bedtime for a lot of you, and I will see you at the usual time in the morning.
Okay.
Okay.
Okay, Jim.
Cheers for now, then, guys.
Okay. Hello.
Hello.
No. I wanted to talk to Mr. Khagendra. So bye.
Okay then.
Easy. Okay. Okay. See you tomorrow, Jim.
Will do. Cheers.
Cheers. Cheers. Mommy, look खत्म हो गई.